2, 1.
Okay, so hello everyone, and welcome to the second edition on our workshop on map-based localization for autonomous driving, which is held this year in conjunction with ICCV. First of all, I want to welcome everybody in the name of all of our organizers, which are on one side, Daniel Krimmers, who is a professor at the Technical University of Munich, where he's heading the chair of computer vision and artificial intelligence. And furthermore, Daniel is a co-founder of Artisense, a Munich-based computer vision startup focusing on camera-based localization and mapping techniques. Furthermore, we have Patrick Wenzel and Nan Yang, who both are PhD students at the chair of computer vision and artificial intelligence at TUM, and also are senior researchers at Artisense. And myself, I'm just recently became a professor at Karlsruhe University of Applied Science, but I'm also still involved in research activities with Artisense. To give you some general information about the workshop, since you are seeing this video, you're either joining via Zoom or via YouTube. So we have here the stream on Zoom, but also a public stream on YouTube. So you can also join from externally. We will have a number of speakers in our workshop. So we will always have invited talks, and then we will have afterwards a Q&A session. A Q&A session where you can ask questions, and I hope we will have some fruitful discussions. If you need further information about the workshop, feel free to visit our workshop page where the URL is given here. Now, what will this workshop be about? So mainly we want to discuss all open questions around the topic of mapping as well as map-based localization. And there I see the most important questions, for instance, if and why we would need maps for autonomous driving. So if we have those maps, how can we keep them up to date? And also how are we able to localize within those maps, basically in any environment, but also under any conditions. And of course, there are also many more questions which we hope to discuss and maybe partially answer within this workshop. Furthermore, we were running with the workshop our second map-based localization challenge based on our 4 seasons data set, which we released last year, and we will present the first and second place in our challenge. So we will have a number of very exciting keynote speakers, which is on one side Wolfram Burgard from the University of Freiburg, as well as the Toyota Research Institute. We will have Felix Heide from Princeton University and a co-founder of Algolux. We will have Alex Kendall, who is a co-founder of Wave. We will have Simon Lynen from Google. We will have Michael Milford from the Queensland University of Technology in Brisbane, Australia. And we will have Torsten Sattler from the Czech Technical University in Prague. To give you a rough schedule on our workshop, so after this introduction, we will start straight with our first invited keynote talk by Michael Milford. Afterwards, we have a talk by Simon Lynen, as well as Alex Kendall. And after those 3 talks, we will have a half an hour break and then start with the second half of our workshop. In the second half of our workshop, we will first have an introduction into our challenge, where we also want to again present our 4 seasons data set, which the challenge is based on. And then we will have 2 talks by the first and second place of our challenge. And after that, again, we will have another 3 exciting keynote talks by Felix Heide, by Torsten Sattler, as well as by Wolfram Burgard, who will conclude our workshop. And before we start with our presentations, I also want to thank our sponsors, which are Artisense and Kudan, who provided us the prize money for the challenge. So thank you very much to our sponsors. And with that, I want to keep it short, and I hope that you are enjoying our workshop, and we will start straight with our first talk. And for this, I want to introduce Michael Milford. I stop sharing my screen. And Michael, maybe you can already prepare, and in the meanwhile, I'll introduce you. So yeah, it's my great pleasure to introduce Michael Milford, who is a professor at the Queensland University of Technology in Brisbane. And furthermore, Michael is there heading the QUT Center for Robotics. Michael conducts interdisciplinary research at the boundary between robotics, neuroscience, and computer vision. And particularly, which also fits great into our workshop, is that he is quite well known for his accomplishment in the development of new technologies in challenging application domains, such as all-weather and anytime localization for autonomous driving. For his research, Michael received numerous awards, including the ICRA Best Vision Paper Award in 2012, as well as a Microsoft Research Faculty Fellowship. And yeah, it's my great pleasure to have you here, Michael, and the stage is yours.
Thank you, Nicholas. Can you hear me okay?
Yes, we can hear you perfectly.
All right, fantastic. I must admit, I got an email a few minutes ago. It's currently 11 p.m. at night in Brisbane in Australia. And I got an email about giving my talk at the localization workshop at ICCV at 6 a.m. the next morning. And so for a moment, I panicked and I thought I was 7 hours off in my calculation and I'd mucked it all up. But then I realized there's a bunch of localization workshops at ICCV this year, one of them separated by a week. And so I guess it just indicates how topical and important this field is currently. But thank you very much for inviting me. It's great to get the chance to give the first talk today. I plan to ask a few questions, maybe provoke a few discussions, and not answer any of them, and hope that the other speakers today can do a much better job of giving their own insights on some of these questions. So I'll briefly introduce myself and the research group that we have here. I'll move on to give some sort of motivating context for some of the grand challenges that we're attacking and many others are attacking in this field around mapping and localization for autonomous vehicles. I'll briefly highlight a few different areas of work that we've been attacking, especially some recent work in this year's ICCV, CVPR, and Coral conferences. I'll spend quite a bit of time motivating some of the questions I want to ask based on some of our many applied projects in the autonomous vehicle space. So I can't talk about all of these, but some of them I can. And there have been some very interesting insights that we've gathered along the way. And then I'll conclude by once again, as I mentioned before, not answering any questions or not answering many of them, but perhaps posing some questions about really what exactly are we trying to achieve in this field of map-based localization for autonomous vehicles and for robots more in general. I should take about 35 minutes in total. I'll try and keep to time or even a little bit less than that. That should give us plenty of time for questions. As an introduction, I come from a center called the QT Center for Robotics. I'm the joint director of it. We have over 100 researchers, and we work across autonomous and robotic systems in the skies, on the ground, and underground, including a large number of autonomous vehicle projects, not just on-road autonomous vehicle projects, but many in a variety of off-road environments, including in defense, in mining, and in agriculture. My group does a lot of research in visual place recognition, localization, mapping, and related areas. We do a lot of biologically inspired research, which I won't talk about today, but very much active in this space. If you want more information, look us up online. We have a bunch of key survey papers where we sort of give our opinion along with a bunch of other co-authors about some of the grand challenges in these areas and all of these areas. So obviously deep learning, semantics, place recognition, localization, they all have varying degrees of overlap. There's open source code for a lot of the research that we do, just look it up. And as you'll see in the talk, there'll be publication references in red at the bottom of each slide. All right, so let's get started with some motivating context. So I like the introduction that was given. in terms of there are a very large number of grand challenges in the area of mapping and localization for autonomous vehicles and robotics. But two that we and many others have been particularly focusing on are these dual challenges of viewpoint and appearance variation when you're trying to create a high performance, reliable localization system. So this is a video I always show. This is from two traverses of a road in Brisbane, Australia. We don't have snow much in Australia, but we have tropical thunderstorms. And so it creates a very severe degree of perceptual appearance change in these environments. You'd have the same with snow and many other types of atmospheric effects all around the world. So appearance change is one problem. The world is always a changing, slow change from construction, cities gradually changing, seasons, and rapid change from atmospheric effects, weather, day-night cycles, all sorts of factors like that. The world is never really entirely static, which makes it interesting, but also makes it difficult for roboticists. The core appearance change problem, of course, is that you have these problems where the images on the left are images of the same place but look completely different, and the images in the middle are of different places but look superficially to be exactly the same place. This isn't the only appearance challenge. There's lots of others, but this concept of aliasing and ambiguity is one of the key ones. Viewpoint change is another big one. Although autonomous vehicles tend to stay in their lanes, there are situations where they won't be in their lanes. If you work in autonomous vehicles in off-road environments, they are definitely not repeating exactly the same route each time. And so you need to be able to localize under significant, sometimes extreme degrees of viewpoint change. And when you combine both of these together, it is particularly, arguably pathologically difficult in a way that many humans can't really solve, and which really challenges the state of the art. So over the years, my group has been attacking this in a variety of different ways, using novel sensing modalities. Why develop smarter algorithms when you can just cheat and use a better sensor is one approach. We do a lot of bio-inspired research, which I won't talk about at all today. Of course, we hit everything with the big hammer of modern learning-based techniques of all varieties, not just deep learning. Novel algorithmic approaches still have a role to play. The use of semantics, of context, of richer understanding of the scene, the use of simulation to augment real-world testing and training, and more recently, the use of physics. So classical models of physics in terms of optics and other aspects can be quite useful. You don't have to learn everything, and in some cases, it really is counterproductive. So I'm not going to cover most of these in today's talk, but I will touch on a few examples of these in terms of some key research areas that we've been working in. So I won't spend much time on this, but we really got started in this area of appearance, robust, at least place recognition, and then eventually localization with this system called sequence SLAM, which is not an actual genuine SLAM system. It's really a visual place recognition system. And this is an example of a simple algorithmic approach to the problem of localization that can actually get you a very long way in terms of doing coarse topological localization. And the idea here was very simple. You have some reference image database or map of a very large city that you're trying to localize in, rather than the convention of the day, which was to find a single global best match for where you might be based on the image coming from the camera on your car. We forced whatever your matching algorithm was to find lots of speculative matches, hundreds of thousands, if not millions of them, forcing it to find a match within every local spatial area or locale in the environment. And then over multiple time steps, looking for spatially and temporally coherent sequences of these matches. And that was a very effective technique. It meant using quite long sequences, about 300 meters of data. We were able to topologically localize or recognize that these are the same places. And this was pretty much, to the best of our knowledge, the first time people had done this, admittedly with very long sequences along very path-constrained environments. So there's some very strong constraints on where this was applicable, but still very useful in a range of applications. We did follow-up work, once again, diving into the bio-inspired aspects where we were able to reduce it from a 300-meter sequence down to doing this matching off just single images. So not needing the sequence anymore, but once again, not having very precise pose estimation or anything like that. This is still very much a coarse topological localizer. So that's really characterized the theme of our research since then. So I'll move on to just highlighting some of the more recent research we've done over the last few years, especially this year. So this was work led by Saurav Garg called LOST, Appearance Invariant Place Recognition for Opposite Viewpoints using Visual Semantics. So what we really wanted to do with this research was push the boundaries on difficulty level. And so people had done severe appearance change data sets with limited degrees of viewpoint change. What we did in this data set, or this approach, using the Oxford robot car as our test data set and some other data sets, was to try and solve the problem of opposing viewpoints. So can a car with a limited field of view camera localize moving along in opposite directions to the reference traverse across extreme appearance change? So this is almost as difficult as it can get. The only thing more difficult than this would probably be if it was a freely maneuvering drone rather than a vehicle stuck on the road. So if you're in an autonomous vehicle company, and several of the speakers are today, which is great, there's no need to solve this problem. This was done more from a scientific curiosity point of view, because you can just use a 360-degree field of view sensor, whether it's a LiDAR or a camera, and that will explicitly bind the forward and reverse directions together. But scientifically, this is interesting because humans don't have 360-degree view sensors on their head. And then also not turning around constantly to reconcile views from opposite directions, or not doing it that much at least. The other appeal from our perspective, and I'll talk about this at the end of the talk, is we're really interested in reconciling the vast differences in how current autonomous vehicle localization and navigation systems mostly work, and how humans drive and keep track of where they are. And I think most people would say that there's still a vast divide between the two systems for all sorts of good reasons. So our approach here was to try and take a more naturalistic approach to localization. And we were interested in localizing based off sequences of semantic cues that would pass by the car as you moved along a road. So the actual technical process was relatively straightforward. We did dense semantic segmentation on an image, extracted dense descriptors on a per pixel basis per semantic class, which you can see in this slide. And then we did this not just for a single image, but for the local sequence of images. So within a local region or local sequence of frames. Within that local region, we computed the mean tensors for each semantic class. We actually focused on just 3 semantic classes out of the, I think, 20 that were in the original system. Computed these mean tensors. And then for each individual image, we computed the mean absolute deviation of that image from those mean tensors. So really a representation of how much each image varied in each class from the average representations of those semantic classes. And then we concatenated this together to form this sort of forced acronym, the LOST, the local semantic tensor. And then we use that as the signature for images. And this is what we use to compare similarity between prospective image pairs, and this gave us a ranked list of candidate matches whenever you're doing place recognition. This wasn't enough by itself to solve this very challenging problem. So what we added was a sort of pseudo feature-based approach. So we used the confi feature map layers, looked at the maximally activated areas of these maps, and used these to form what you'd call very speculative features, or key points, sorry. And then we used these key points in the 2 images in a speculative image pair, compared how similar they were based on their location in the images, weighted by whether those key points were in the same semantic class and by the pairwise descriptor distance. And with all of that put together, we were able to recognize that these were the same places using a sequence of images, not just a single image, but despite the fact that the reference traverse was facing in the opposite direction to the query traverse. Now you can see the precision recall curve is not particularly crash hot. It's not as good as you'd expect for sort of some of the more standard tasks, but it was performant to some degree. And this was sort of upping the difficulty level in this sort of area. So one of the follow-on works, and this was presented at CPPR early this year, was a system called Patch NetVlad, which really learned from many of our observations from a lot of the work we've been doing in this field. And the key concept here was to combine the concept of local and global descriptors for place recognition, fairly precise place recognition. So we're running this through some of the more standard computer vision benchmarks and metrics for assessing performance. So the original NetVlad system is still annoyingly good. It still benchmarks quite well. But what the idea of this work was to build on top of it. And the core concept was very simple. There's really only two components. Rather than doing a global descriptor, what we did is what we call locally global descriptors. So we're doing this on a patch-based basis, but it's the same overall process and doing this over multiple patch sizes. And then to compare patches, we did patch-to-patch comparison. And then to make this actually work, we had some sort of geometric verification step using a variety of different approaches. And so this system worked quite well. It wasn't the best across the board, but it was competitive or superior across a number of the benchmark data sets. And I'll talk about some of my issues with benchmark data sets in the last part of the talk. We had optimized versions of this. We did ablation studies. I won't really talk about this in much detail in the interests of time, but it was relatively stable in performance for different parameter values. And we had very high-speed versions of this, so versions that could run at real time on moderate compute, while only dropping a very small amount of recall performance. Obligatory qualitative results showing some of the correspondence pairs that the system was able to find between some of the classical data sets that everyone runs on, including from the Tokyo data set, and then a real-time demo just from our labs in relatively challenging lighting, not really optimized or anything, but just giving you an idea of how it works. And so this is all open source. It's reasonably popular on GitHub. Go check it out. Download it. It's fairly actively maintained by the team. All right, before I move on to, I guess, some of the application areas, I'll just highlight some work that's been presented this week. So I mentioned that we use at least 7 different approaches to trying to solve this problem of viewpoint and appearance invariant localization and place recognition. So this is work performed by Attila, who was a visiting student with us during his master's, is now at TU Delft, I think. And this was the idea of using physics. So I said you don't have to learn everything. Where you have useful physics priors about things like illumination and other factors, you can bake it into your model. And so the key idea of this work, and I won't go into any detail because Attila is presenting it at ICCV as an oral, is to put color invariant edge detectors as an initial input layer into a CNN. And the idea is that this creates a more or somewhat more invariant representation in terms of illumination change. And you can see in the column graphs at the right side of this slide, the baseline system going from normal to a darker scene. You can see there's a larger shift in the distribution. In the second row of column graphs, you can see that with this proposed system, there's less of a shift, I guess, representing the fact that it's a little bit more invariant, not completely invariant, but improved invariance to illumination changes. And this is work led by Saurabh Garg, which is being presented as an oral at Coral in a few weeks' time, online for us, but I think it will be held in London. And this is the idea of really doing a more rigorous approach to sequence matching in the area of place recognition. And the whole core idea here was to do sequence matching based on triplet loss, but to do it with some constraints so that you're using the temporal order of the places that you're matching and limiting, I guess, the pairings of those to the positive examples and negative examples. And that leads to a substantial performance improvement, rather than treating everything on a frame by frame basis, using the sequence matching process itself to shape how you do this whole process. And Saurav will present that in far more detail at the conference. All right, so I wanted to leave plenty of time to talk about the application areas that we're working in. So we work in a lot of application areas, only some of them are autonomous vehicles, but I think they're particularly interesting because we work with government on assessing autonomous vehicle tech. We work with some of the leading automotive companies, although I can't talk about that at this stage. And we also work in off-road autonomous vehicles in mining and defense. And the group more widely works in areas like autonomous vehicles in agriculture. So we have a lot of experience in the autonomous vehicle space, not just in on-road, but also off-road. So one of the projects was a project with Caterpillar, Mining 3 and the Queensland government, where I come from, on providing a couple of different vision-based or multi-sensor-based localization systems for autonomous underground mining trucks. This is called a load haul dump truck. So it's equipped with cameras. It can be equipped with LiDAR or single plane, multi-plane lasers. This is what this environment looks like. So it's very different to a road, very geometrically aliased. Everything looks very similar. And very visually similar as well, not just in terms of LiDAR range sensors, but also in terms of vision. It's also very challenging. These are some of the perceptual conditions that you encounter underground. There's water, there's dust all of the time, there's glare, there's low light situations where the lights go out. So it's an extremely challenging perceptual environment for an autonomous vehicle to work in. So one of the things we learned in these industry projects is that some of the time you just can't localize. And so you need, this is a very simple initial approach to this, but you need to be able to work out when your system is just not going to be able to function. And that requires it to be able to intelligently assess the sensory input coming in and work out whether it actually has any chance at coming up with a valid localization estimate. This deals to the whole issue of introspection or self-assessment. Knowing when you don't know is critical for autonomous vehicles, especially in the localization space. Just some sort of incidental photos. These are the sensors, very different in some respects to what you see on an autonomous vehicle, on-road autonomous vehicle. This is the rig in our lab before it went out in the field. This is the rig after just a few days in one of a variety of mine sites around Australia that we tested in. You can see it's very dirty. People have to clean it regularly. Here's another shot just showing how much dust and other things get on these sensors. And you can see how big these vehicles are. This is quite a large sensor rig, and you can see that the very large load haul dump truck makes it look very small. And one of the things we learned, and I think autonomous vehicle companies have learned this too, is that fully autonomous SLAM is often not really the best way to go, and semi-supervised SLAM with some degree of human supervision and annotation and correction is actually more efficient overall. This is especially true in underground environments because you don't actually have ground truth. There is no perfect surveyed millimeter accurate map of the mine because it's not technically feasible. And so you have to do the best with what you can. And that often requires a mixture of autonomous mapping and supervision and annotation and correction by humans. This is one of the final experiments that we ran that we can show you. So this is the vehicle going into, this is not in autonomous mode, but the mapping system is running going on a 5 or 10 kilometer journey deep into an underground mine, about 600 meters underground. And this is the multi-sensor localization system that we developed, which is using both the camera and the LiDAR sensor localizing throughout this whole journey. And we ran 6 sets of field tries across 4 mine sites in Australia. Some of the interesting things we learned, and this is a common theme in autonomous vehicles on road, as I understand it, not all errors are created equal, so it's very task dependent. In these underground mine sites, your longitudinal error or downtrack error, so this is the error in your positioning estimate along the length of the tunnel, is often not very important until you get to a junction point or get near a T-junction, for example. The lateral or cross-track area, so this is where you're located laterally or sideways across the tunnel, is critical, because if that's off by too much, you drive a 20 or 30-ton vehicle at speed into a hard rock wall, which is not a good thing for anyone. And so this, I guess, has broad relevance that not all errors are created equal, and not all errors have equal significance for different types of autonomous vehicles. Not only that, but not all sensors have equal errors. So if you look at the particle distributions for the laser and the camera, you can see the laser is very good at giving you lateral accuracy. The camera is not so good at that, but it is better at giving you longitudinal or down track accuracy. And this behavior would be different for an autonomous on-road vehicle, and is from our experiments. But the important thing is that different sensors have very different characteristics in terms of what localization accuracy they will give you, and how you fuse them together is of utmost importance. The second applied project I want to talk about is one that's a little different, I think, from a lot of typical talks you get at these conferences, which is we've been working extensively with various transport government agencies in Australia, including the ones on this slide, to assess the likely impact of autonomous vehicles were they to become widespread on Australian roads, for example. It sometimes feels like most of the autonomous vehicle revolution is happening in California and a few other select places around the world, but a lot of countries are very interested in how these technologies might unroll on their roads. So we had a large team for this project. This is a vehicle that we developed from scratch. So this is built off a Zoe electric vehicle. This vehicle is called Zoe 1. You can see the sensor rig. This particular car is not autonomous. It's a research platform, but there is also an autonomous version, sister car of this car at QT, which has limited level 4 autonomy for research purposes. We grabbed 1,200 kilometers, so about 700 miles, 750 miles of data, rural, urban, all conditions, day, night, pretty much to capture the range of conditions that the vehicle might encounter. Roads with line markings, roads without line markings, which are quite common, especially in rural Australia, really giving a great data set for capturing the range of conditions the car would encounter. What we did is we evaluated the competency of the state-of-the-art algorithms and techniques that were in the public domain. Obviously, proprietary companies have a whole bunch of magic stuff that they keep behind closed doors, but this was in terms of what was publicly available. And we looked at traffic sign detection, traffic light detection, line marker detection, localization, and positioning technologies, and particularly the use of prior maps for improving the performance of sign detectors and traffic light detectors, which very much plays to the topic of this workshop. So line detection, usual story, using modern learning-based systems, it works pretty well. Street sign detection, use not a fairly conventional pipeline. This is a sort of different performance graph to what you're probably used to seeing, but this is the performance of the detector at detecting 4 different signs. So the 4 different groups along the bottom of the x-axis. Blue is ground truth, the number of occurrences of that sign in the data set. Green is what the algorithm picked up off the shelf without any local training, and red are all the false positives. So you can see the system basically fails horribly out of the box. And this is true of most systems out of the box in an environment they weren't trained for. All right, so that's what I just described. All right. We trained it for Australian conditions, so trained it on data sets we gathered of Australian specific signs, because part of the issue was some of the signs in Europe had never been seen in Australia and vice versa. And that improved performance, but you can see there's still a very significant false positive rate. Lots of reasons for this. You get signs that are out of context, signs on this wrong side of the road. You get signs that the car has never seen before. At nighttime, it can be quite challenging to see signs. Certain lighting conditions can make it challenging too. Traffic light detection, same deal. Performance, once again, the red bars are too high. That's the false positive count. Red bars are way too high. And you can see many of these sort of out of context traffic lights being combined together, petrol stations or fuel stations being detected as traffic lights, and so forth. Rain on the lens of the camera, and the traffic lights from a train line being detected as traffic lights on the road. So what we did is we dived into using prior maps, so prior high definition maps. Obviously, we don't have the resources of a trillion-dollar tech company, but we did our own implementation of these. And this is the key takeaway. So when you have access to prior high definition maps, which is the performance bars at the rightmost of this graph, your performance improves by many, many orders of magnitude, and your false positive count drops to almost 0. So we found in our studies that prior maps make an incredible difference to the performance of your other systems on your autonomous vehicle. Of course, maps are not everything. When you do your mapping runs, things can be obscured. These are some examples where trucks were blocking certain lights, and so they weren't in the reference map. If you have hundreds of thousands of vehicles permanently on the roads, then you have effectively real-time surveillance, and this would be less of an issue, but we're not at that stage yet. We also did other projects looking at all the other considerations of mapping-based solutions for HD, for autonomous vehicles. There are a huge number of data formats across different municipalities, across Europe, across Asia, across America, not always the same. There's the fact that map updating, maps can be inaccurate, reality can change, you can have localization errors that corrupt your maps. And when you update your maps, you can corrupt the map if you don't do it well. There's different levels of dynamicism. There's very temporary things like pedestrians, cyclists, and cars, all the way to long-term construction change. These are all very difficult problems and arguably not yet solved. And then in terms of how you solve it, there's all the different communication workflows at the bottom right of this graph. So the Government Transport Authority will have access to some of the change information about roadworks. The private providers of HD maps will also have some information, and then the vehicles out on the road will also be driving around. And so there's the whole issue of what communication channels you have between all of these different stakeholders to keep your maps as up to date as possible. So all of these are available in full detailed reports. You can go look them up. I think we'll probably share the slides from this presentation. And another observation we had from here was, once again, knowing when you don't know is more important than knowing. So a very contrived example is you have a positioning system for an autonomous vehicle that works 99.9% of the time, but when it fails, it doesn't realize it. And you have another positioning system that works 99% of the time, but of the remaining failure times, 99% of that time, it's aware that it's failing. And that system too is actually better because it only acts confidently off incorrect information 0.01% of the time, 10 times less than system 1. And so it's not just in the benchmark numbers that you see in papers. So I think I'm going all right for time. What exactly are we trying to achieve? And this is some opinion. I am not going to answer most of these questions. As first speaker, it's my right to ask questions and not answer them completely, but we'll see how the workshop develops. So the understandable and honest answer, and we're as guilty of this as anyone else, is I'm trying to get my next ICCV, CVPR, et cetera, paper accepted. So I need to outperform the benchmarks, et cetera, et cetera, et cetera. But really, that is not the ultimate motivation for any of this, right? And when we look at how human drivers drive a car compared to an autonomous vehicle, humans driving a vehicle do not have millimeter accurate positional knowledge. They have a very different sensing suite to a typical autonomous vehicle, with the exception of cars, maybe like Teslas, arguably. They drive well in environments they have no prior maps for, which is different to most autonomous vehicle approaches, and they have amazing practical common sense. If you look at prototypical AV solutions, very complex, rich, multi-sensor suite, often using very precise prior HD maps, relatively limited contextual and semantic information, like they have it, but it's not as sophisticated as what a typical human driver would have. And their intelligence is limited to some degree. And so really the question is, what localization metrics will best further progress in this field, given that currently autonomous vehicles don't drive like humans, but perhaps this gap will gradually decrease over time, or maybe it will increase. I don't know. I don't think anyone knows for certain. Mapping is a means. It's never the ultimate end. All maps are there to be used for something. The map is of itself of no purpose. That's one thing that we always try and remember. Current localization metrics, which are what get you that CVPR or ICCV paper, can probably be improved or complemented. There's a whole bunch of other measures various groups have proposed over the years. How far the car travels without good localization. Is it able to perform introspection and work out that it's not working? Does it have generality? And can you quantify its viewpoint and appearance invariance? And on that front, some good progress has been made. So I've only listed 2 here, but there's a bunch of quantified benchmarks out there now, which is helping us progress in that area. And really, how can we better connect the goals driving research in this area? So what is driving the research field with what's actually useful in the end applications in autonomous vehicles? So as a recap, I talked about the grand challenges that we and many others are trying to attack. Talked about some highlights of some recent research in this area, gave a few insights from our projects in the autonomous vehicle space, and then recapped with some key, I guess, framing questions for what are we really trying to achieve. I have a vested interest in this area because we're taking a sort of long-term approach to this. So we have a long-term project running until 2027, which will have a very large team of researchers. And we are looking at positioning systems, mapping and positioning systems for robots, for autonomous vehicles, and all other systems. And you can see the 4 themes of our approach is not just about getting 99.87% on benchmarks. It's about making sure that these systems are auditable, that they're explainable, that they're functionally relevant to the task that the robot or autonomous vehicle actually needs to perform, and that they are, as where possible, compliant in terms of privacy and in terms of cybersecurity. As a result of that, myself and my colleagues were always recruiting. I think I need 4 or 5 postdocs in the next 6 months, and we're hoping the borders will open up shortly and everyone will be able to come to Australia again, which will be fantastic. So once again, thank you very much to the organizers for inviting me. It's very, very good to see a workshop of this nature at ICCV. Feel free to reach out if you have any questions or want to chat about anything. And I think we have 4 or 5 minutes now for questions. Thank you.
Okay, great. Thank you very much, Michael. Thank you for the very interesting talk. Yeah, to the audience, feel free to ask any questions, either here in Zoom in the chat or in the chat in YouTube. And I hope we can answer all of them. Yeah, in the meanwhile, if we don't have a question from the audience yet, I actually would personally like to ask you a question, which is about the entire pipeline of localization. So currently we have more or less, we have a place recognition module and we have an odometry module, and then the results we more or less put together to get maybe centimeter accurate localization. So therefore my question to you, since you are quite focused on the place recognition task, on the image retrieval task, how could we get both closer together such that they better actually could benefit from each other? So how odometry could benefit from place recognition, and on the other side, place recognition could benefit from the odometry. Yeah.
Sure. And I think you're anticipating what is already a rapidly growing research area. And I think that's going to explode at the robotics and computer vision conferences in the next 12 months or so. The key aim, I guess, is to make sure that the complementary strengths and weaknesses of motion estimation systems, whether it's IMUs, whether it's odometry and encoders, whatever it is, complements the coarse and fine loop closure / place recognition capabilities you talked about. I guess the key challenge there, one of the key challenges is the fact that, yeah, as you said, we're just bolting these systems together, usually with topological localization followed by either filtering with motion estimation or the pose refinement stage. I think the key will be to work out learning schemes that integrate these more closely and that jointly learn the best parameters and best frameworks and best configurations given how the others work. And we are starting in our group to scratch the surface. Saurav's work that's coming up at Coral is an example of that, where you're explicitly taking into account the sequential matching process in your overall system. But we have a number of other areas of research that we're looking at that's trying to bridge that gap, as you mentioned.
Mm-hmm. And so in the end, you think we will have also a network which maybe is able to predict us centimeter accurate localization, or you still think we always need the filter in the end, basically?
Oh, you mean just straight off the bat, off a single image? Can it look?
I think rather I think of a sequence of images that it gives us in the end an accurate pose, basically, rather than just a candidate in the map, more or less. Right?
Yeah, I think so. In the same way that these two level hierarchical systems are shown very comprehensively, that as long as you have 100 or so topological estimates to seed your pose refinement stage with, you almost always get a very nice, fairly precise match. I think when we bring in the sequential matching more organically into that process, I think you'll see the same thing happen again. It's just a question of the technicalities of how you do that well.
Yes. Okay, great. Thanks a lot. Yeah, so I think we don't have any further questions at the moment, but yeah, also feel free to ask any questions at a later point, and we try to forward them to you, and we hope that you are able to answer them. Yeah, and therefore I want to thank you very much again for your very interesting and exciting talk. And with that, I will hand over to my colleague, to Nan, who will introduce our next speaker. So thank you very much.
Yeah, thank you, Nicholas. Also, thanks again for Michael for the impressive talk. And it is my great pleasure to introduce our next speaker, Simon Lynen. And Simon Lynen is currently Senior Staff Engineer, Software Engineer, and Tech Lead Manager at Google Zurich. Simon previously pursued his PhD at the Autonomous System Lab at ETH Zurich, with a focus on visual navigation and localization algorithms for robotics, mobile devices, and autonomous cars. His group at Google develops a visual positioning service, namely VPS, which provides low latency, high precision image-based outdoor localization. VPS has enabled the customer devices to have location-aware appearances at global scale. In parallel, VPS has grown into Google's platform for localizing and semantically annotating various large volume pixel sources, such as from Google Lens and Photos. It is our great pleasure to have you here, Simon. The floor is yours.
Cool, thanks a lot. Can you hear me fine?
Yes. Yes, we see the slides now. I think you are muted now, Simon. Simon, I think you are muted now.
Okay, I'm sorry. This is the
now it works. No problem.
This is the auto presentation. Cool. Thanks for the introduction. I'm going to talk about VPS, which is Google's system for visual localization. Thanks, Michael, for all the industry prefix. I think that's quite nice to see that SVMs and particle filters are still used elsewhere, so it's quite nice. What I want to talk about today is, why does Google care about visual localization? I want to go a little bit into depth what we are doing in my group, and also want to talk about the remaining challenges. I mean, I think many of these are known. I put a night image on the right. These things are working, I think, these days quite fine, but there are many cases, obviously, that are, still really quite hard for visual-based localization. As a very quick intro, I think we all know phones have GPS and phones have compass. So in principle, one would imagine this problem isn't something that we need to still solve. But in reality, we have multipaths from GPS that you can see here in this picture on the right, where satellite signals are reflected multiple times before they hit the phone. And then the compass is really quite small inside the device, and whenever you have a car or something nearby, it gets disturbed. So what happens in reality is that if you look at your phone and you look at Google Maps or Apple Maps, you see this blue dot move around quite a bit. And one thing we wanted to do a couple of years ago is to actually use visual localization against Street View, which is this very large corpus of imagery that Google has collected over the years, and enable a much better experience. So certainly sub-degree orientation and sub-meter positioning. And you can see this launched as a product, I think, about 2.5 years ago now in Google Maps, where you can go on live view and you can basically localize within about a second, a little less, and then you can get these very precise information about where you want to go. This also works indoor, which I think is quite useful for many people because we have these larger and larger structures in airports and malls. And it's getting quite difficult, of course, if you are traveling again to find your way around. And we have been launching things at Tokyo Station, which you can see on the right-hand side, or in Zurich train station and at the airport, and in other venues as well in the US. The other thing that VPS is obviously useful for is, vehicle localization, which is the topic of this particular workshop. But if you think about infrastructure monitoring, localizing dashcam videos, or just doing like Google Lens and photo localization, these services can be really used for a ton of different applications. And as also mentioned in the introduction, the service my team built is now used at Google for a relatively large stream of images. So there's like hundreds of millions of images localized every day against the system. Because I'm in industry since a while, so a little bit detached from academia, I think for a couple of years now, but I think one value I can probably bring here is give you a bit of an insight into like how you can scale these things. I wouldn't say that like everything that we do is like just commodity and old style. I will go a bit into where we are investing into quite modern approaches, but still scaling such an approach is a huge challenge. And I think it's also important to be aware of this. Because that what ultimately matters if you want to bring things to like the user or like to a real application. So today I will talk a little bit about how we built this like underlying model and the map, and then I will talk a little bit about the online component of this. So like how do we actually take a GPS signal, for instance, and then match features against this model and do outlier filtering and resectioning, and how do we verify the final position if we want to return to the user. So really like an offline stage and an online stage is what also is important in our system. So everything we do is based on Street View. You've probably seen these kind of backpacks, or you've seen cars drive around your city. So what we have been doing over about 10 years is go basically every street that we are allowed to drive from the governments over the years, multiple times. We have been also carrying these backpacks in like kind of side valleys and so on. So we ended up with this like pretty vast coverage of imagery data. So this is what you can see publicly. You can zoom in here, and I'm based in Zurich, so of course I'm going to show you a little bit how it looks like here. But you can already get at a glance that like many streets are covered. We are not allowed to publish all the images in some countries, but like we have basically driven every single street in these countries. So I think it's not really important to explain this, but like Street View is just comprised of these panoramic images. They're sampled every couple of meters, and you sometimes find very large baselines, like in this approach here or in this situation. But most of the time, you have fairly good sampling over the environment. So what we do at Google is we take all of this data and then we run a very large structure for motion over it. In fact, like there might be a bunch of collections from an entire continent being bundle adjusted together. So like what you get in the end is like this one single consistent model where all the captures are aligned to another, independent of any GPS errors you might have seen initially. Like afterwards, it's consistent, and it's like one structure for motion model that is geo-aligned and basically spans the entire planet. So what we do with this is we basically get like pieces of that model, and I will talk about how we do this in a second. And then what we have is not only these points, but really like a very dense view graph. And on the lower screenshot on the right, I've shown you a typical key point in our SFM models where a 3D point is associated and observed from dozens and dozens of viewpoints. And we really can not only determine the visibility of the point, but also like the appearance from many different viewpoints. The system my team is running is relatively large. So as mentioned, we cover many countries worldwide, indoors and outdoors. We index a little bit more than 100 billion images. We have an SFM model that is, after compression, about 4 trillion 3D points. And then we have about 10 trillion visual descriptors on this. And I will talk about why these two numbers are so close together in a second. So one thing that you will see if you build such a system is that just storing the SFM models is relatively infeasible, like even for a large tech company. So if you think about the SFM models we have with 1 million, 2 million 3D points, you can easily end up with hundreds of megabytes of storage. So what we need to do is we need to run very, very aggressive compression so that these models get small and we can actually serve them in real time. Remember, most of our users want to have immediate feedback, so we can't load something from disk that takes seconds or even minutes to load. What we do here is pretty classical. In fact, we run kind of very old, like now it's nearly a decade-old approach where we subselect landmarks based on how informative they are. So you can put different scoring functions in there, but at the foundation, this is all like kind of observation count or visual saliency. And then we run just a set cover problem where we pick the points that we think are most likely to be observed in the future. But what we do based on top of this is that we have a learned embedding that takes all the descriptors of a particular 3D point, and we summarize it to a relatively low dimensional descriptor. So in this particular case, we might pick 1 or 2 or 3 descriptors per 3D landmark, and these are only 16 dimensions. So what we do is we really compress down the view graph and also like the appearance that we want to keep. We then chunk this problem up. There is a library that Google open source called S2 Geometry. I think Uber has one with hexagons as well, but at the foundation, this is just allowing you to spatially shard and split up your model. So we do this with about 150 by 150 meter areas, and when you want to localize, you load the stuff near your GPS, and then you localize against that. And it takes typically about 150, 250 milliseconds for a query to be successful if the GPS prior is 100 meters off or something. There's a lot of that technical detail that I actually published last year in an IJR paper. So if you're interested, you can take a look at it. The other thing that I think is really important and has received a lot of attention over the last couple of years is learned feature descriptors. So as you can tell, running an SFM, you need features, and obviously there has been this huge history of handcrafted descriptors, but we have also seen over the last couple of years that there is a large amount of performance to be gained by using learned features. So this is one of the bigger investments we are doing in my team in terms of kind of building a more modern stack. One thing that was really important for us when we looked into this topic is to leverage as much as possible of Google's previously collected data. So at the center of all our learning is to use geometry for supervision. So what you can see on the top are 2 images collected at different times of the year and the corresponding depth maps. So what we do here is we can project pixels from one image to the other using this depth information. And as you can see on the center right of the screenshots is that we get really these like pixel accurate correspondences, or even subpixel in some cases. So what we can do is very direct supervision over white baselines and seasonal changes that allow the descriptor to really learn directly what is important. This is a high-level overview of what we do. So on the left-hand side, again, we train everything on image pairs. And then you can see in the center the network we have, which computes detection scores and descriptors. And then one of the losses we employ is derived from these geometric correspondences that I talked about. So depth correspondences come in, and they form one of the losses that we use for training. The architecture is a pretty standard unit. I will talk about one of our publications later, so you can take a look in detail what we do. But the key here is really that these up and down convolutions give our features a lot of context. So they can do pretty crazy things, as I'll show in a second. This is a typical score map that the network outputs. So you can see here high and low scores and the top selected features. So we typically extract about 2,000 key points, fairly low resolution images, and then we use them for matching and SFM. I want to talk a little bit more about the supervision. So as mentioned, we have these LiDAR points or LiDAR maps between the 2 images. And one of the things you can see in this video is that they give us these very different viewpoints and depth maps. So if you compare these 2 images in the middle, you can see that some of these viewpoints are very different scenes. But LiDAR can really tell us or allows us to pick very hard or very simple use cases or pairs, and then directly supervise the network with it. So what we do here in essence is that we want to have repeatable key points. So obviously, like if you move the camera, the same key points on the same physical structure should be detected. So repeatability of key points means that the score in one of the image needs to be the same score at the corresponding pixel in the other image based on the depth correspondences. And then the other thing that we want to achieve is matchability of the descriptors. So basically just saying that the two descriptors on the corresponding image locations in the two images should have a very low distance. And we use here a standard triplet loss. So again, you have pairs of image pixels in the two images and negatives that you sampled based on hard negative mining. And then what you want is you want that there is a key point in both images and that the descriptor distances are meaningful to you. So A and B are closest, and then A and C and A and D are actually further away than your correct pair. The other paper that we published earlier, and if you want to learn more about what we do, you can take a look at this paper, is the DISC paper from NIPS last year. So this is joint work with EPFL by Eduard from my team. And the main goal that we had here is to solve this chicken and egg problem, right? Like repeatability of key points so that then you can match descriptors correctly, or having good descriptors so that you can match the key points correctly. And this is obviously like an optimization problem that's discrete, but we relaxed it, and then we supervised it using epipolar matches. And the entire thing is formulated as a reinforcement learning problem, and you can see that it really performs quite well. And it's also using a UNet and gives us good matches even over IP interchanges. Here you can see some more examples of our approaches. What's remarkable, I think, here is that the features that we are currently working on are very low dimensional. So you can see that we might not get as good performance, for instance, as Superpoint, but the feature is only 16 dimensional compared to 256 of Superpoint, which has, of course, tons of implications for runtime. So after this, I want to take a quick look at localization and what we do there. So the pipeline is pretty classical. And if you look at the IJR paper that we published, you can see that we are still doing like nearest neighbor matching of the descriptors between the query image and the structure for motion model. Then we do basic outlier filtering using geometric voting techniques that have been published also previously by people on our team. And then we do Ransack and minimal pole solvers. So for instance, like a P3P, or if we don't know focal length, you would run a P4P. And then we have a learned classifier in the end that tells us if a particular solution is correct or not, which goes back to what Michael said about the system needs to know how confident it is. The nearest neighbor search is relatively simple. It's using a joint cost of descriptors and feature orientations, geometry and location priors. So we have a way to combine all of these together in like a single nearest neighbor search. So you're most likely to get matches that geometrically make sense and that make sense together with the location priors that we have and the orientation of the camera. This is helping a lot over just naive matching of descriptors, but there is still a ton of outliers. If you think about large-scale scenes, you have repetitive windows or houses even that are replicated down the street. So the other thing that's really important for us is to filter out these outliers before we run Ransack. And what we do here is we use a voting technique, and I want to quickly explain how that works. So imagine you have these points on the left-hand image that are in these colored circles, and you can see the same points here in the center image, plus you can see where the camera was when it took that image. And you can imagine that for each of these points in the model, we know where it was observed from. So we know which street view cameras, for instance, have seen the tip of the church, or which have seen a particular window. So what we can do is we can reason about these kind of visibility cones for each of the 3D points. And then you can imagine that if you do this not only 4 times, but thousands of times, you will get like an intersecting area of all of these visibility cones that gets sharper and sharper. So all the way down to, let's say, like giving you an uncertainty of 5 by 5 meters of where your camera has most likely been, given that you have observed a particular set of features. This is output from Bernhard on my team, Bernhard's paper from now 6 years ago, but like the principle is quite similar to what we're running today. So you intersect all of these visibility cones, and then you get like a PDF over location of where you think your camera is, and you can intersect this with GPS, for instance, or you can then, as I mentioned, run Ransack on top of this. The key here is that this is very effective in terms of outlier rejection, even if you really increase the scale to thousands or millions of points. The final thing we do in our system is that we try different possible locations. So what often happens is you have repetitive structure, like in this particular scene, where you have a building that is repeated. You have the same window 50 times, and GPS might give you a bit of signal of where you most likely are, but in the end, you still have to try multiple locations. So what our system does is it will take many of these outlier filtering hypotheses and run Ransack on all of them, and then run our learned classifier on them. And in the end, you will get like a ranked set of candidates that are most likely correct, and then you can return one or multiple of them to your client. And you can see this on the right-hand side, that we have kind of this ranking, and we have different errors to our ground truth. And the goal is obviously that the classifier picks the right one that is closest to our reference. So talking about reference, the entire ground truth problem, or the question of how to evaluate, is a big one. And at ICCV this year, we see actually a paper by Torsten, Sattler, and Eric Brachmann on this topic, which I will talk about in a bit. But I think this is extremely important, and we have not seen, in my opinion, enough focus on this evaluation or tuning topic in the past. And we have seen at CVPR last year papers where the data set really influences what method is ranking best, and in localization, that's certainly the same case. What you really want to have are images like this here, which are, they are solvable by our system today, but they were certainly very, very challenging over the last couple of years. So partial occlusions, day-night changes, other scene changes, and so on. So being able to sample from these and generate reliable reference poses is, I think, a key challenge that I want to talk a little bit about today now. So one thing we have in our system is, very early on, we invested into video recording using just regular smartphones. So we had people walk around, record video with GPS and inertial measurement data. And to date, we have about 180 million such images organized in about 500,000 sequences. And all of these are registered against our model. So what does this mean? It means that even for images that are at night or that are partially occluded, that we can't localize individually, we always have a coarse idea of our ground truth or reference poses based on the trajectory alignment. And I think this trajectory alignment is really a key to being able to reliably tune and generate training data, is because it gives you all these very, very hard samples that you don't get if you generate, for instance, ground truth through SFM, which many people are using. If you use SFM, you're basically saying that SFM is correct, and all the other methods, such as scene coordinate regression, are going to have a hard time to meet that particular positive sampling of your ground truth generation algorithm. So again, here the sequence posing is really important. So this is, for instance, a set of our sequences here from Paris. So you can see that we actually walked around quite a bit. So we had operators carry these phones, and we basically did street view tasking. So we asked them to cover nearly every street. So if you zoom in here, you can see that the blue trajectories are all well aligned, and we have high confidence ground truth or reference poses. And then you have gray areas that I will talk about in a second, and red areas. So this is a particular sequence here with the purple sequences where our system is not confident about the reference poses. And typically these sequences are gray, and you will see in the screenshot other parts of other sequences that are also gray. And these are sequences where our reference pose generation is not very confident, and it basically marks them as true as negatives, and then the algorithm can try to localize them, but they will not be counted, and they will immediately go as negatives and hurt recall. So what you want is that your algorithm for alignment is increasingly becoming better at aligning these, but with sufficient confidence. And I will talk about how we do this in a second. So this is an example sequence here where you can see on the lower left-hand side a map view where we have a trajectory from odometry, so standard visual inertial odometry, and then GPS alignment. And you can see that it's fairly accurate, happens to be on the wrong side of the street. But in general, you could use this for, as a reference pose. If you allowed for 20 meters of error or something, then you could use it. But the key now is to use alignment against our SFM model at key points in that sequence, and then be able to completely or jointly bundle adjust the sequence against our reference model. And what happens is that even though there is a couple of parts of that sequence that we can't reliably register, there are many parts of the sequence which are very hard for localization, such as the left-hand image here with the construction site, or even perhaps the right-hand side image with this column, where you want to have reference poses from odometry so that you can try to improve on these cases. What we see if we look at the underlying registration algorithm of this is that there are a ton of outliers in our system. So the system is often actually generating wrong reference poses. And what's important here is to filter out the right ones and then not use these wrong poses that we have computed from SFM or registration as a golden pose or as a reference pose. And you can see this happening very often in academia, that people just run single image SFM, and then whatever comes out with enough inliers is considered good. But the number of inliers is not particularly informative for this particular alignment problem. Here's a sequence that is very well aligned. You can see that the alignment errors are typically about 70 centimeters in the center graph, and then some parts of the sequence are not as well aligned, and we would mask them. But in general, the majority of the sequence is very well aligned, even if there is buses in front or heavy occlusions. And exactly having these difficult cases is important to be able to end-to-end tune your system or generate training data that is actually hard. Here's again a sequence view of that, and you can see it's much cleaner. There's a couple outliers, but the majority of the sequence is well aligned and self-consistent. So I talked about this paper from Eric and Torsten earlier, but there are two statements in there that I just want to emphasize. And the first one is that it's really important that if you develop a new algorithm, that you actually generate the golden reference poses using your own algorithm. So you might think this is crazy overfitting, but what you otherwise are doing is that if you want to beat classical methods, you are going to have a hard time, because all the reference poses that are provided by the authors of the data sets are computed using these reference algorithms that are like a decade old. So what Eric and Torsten propose is to use their own algorithm, and I can confirm that this works really well. Like in our system, we actually run this realignment as part of the training loop. So when we do tuning of the system, we actually realign the system, the sequences continuously. And then the other one is not to try to beat or to measure performance based on pose accuracy, because most of these reference poses are not actually that accurate. And trying to beat another algorithm by another centimeter outdoors is probably not really meaningful. You can see even after very, very heavy engineering, we still have about 20 centimeters of error in DPS in the mean. And there are errors which go all the way up to about a meter. So you really don't want to set a threshold that decides based on a couple of centimeters. We also published some of this data sets if you're interested. So Eduard made a workshop at CEPR this year, which takes some of these image pairs that we've collected with smartphones and makes them publicly available for benchmarks. So I encourage you to check that out. The last thing I want to talk about is how we started moving away from just localization. So if you read, what happens in industry or what Elon Musk says or something, then many people are thinking about unifying the map that you use for localization with the map that you use for reasoning. And we are doing the same thing here in that our localization map is also semantically annotated. So what we do is we use different signals, for instance, like image-based semantic segmentation that you can see on the top left. And we annotate our SFM point cloud with this. And then perform additional processing on it to get the points, crisper and to understand related classes. And the other thing that we do is we run certain image-based detectors, for instance, storefront detections. And then we start labeling our point clouds with the semantic information. So we know which SFM point cloud belongs to a particular store or a sign or a building. What this is useful for is mostly for some of our use cases in photos and lens. So if you want to hold up your phone and you want to understand what the building is, then we localize you, but we also tell you which pixels in the image belong to a particular building. So what we return is something like this mask here in the center, which shows you roughly the outline of a particular building and the semantic meaning. So like, what's the name of the building or which business is inside it. We launched this in a couple of products where you can try it. So for instance, if you do Google Lens queries, you will be able to see these gleams on top of the building, and that's served actually by VPS with the semantic index underneath. Or if you take photos outside, then after a while, Google Maps will ask you if you want to donate them, to a particular business, for instance, and that association is also done with VPS. And then after donation, these images are going to show up in Street View, like you can see on the right-hand side, where you can see these, pins of photos that are correctly localized and associated to a particular business. So to wrap up, the main things that I think are still open are the same ones than 5 years ago, unfortunately. So it's still feature detection, feature matching, the entire ranking problem. So like which candidate pose is the correct one, the right one, the one on this side of the street or next to you. There's a couple of kind of new challenges that I think arrived in the last couple of years, which is everything around 3D semantic scene understanding. Temporal modeling is still a big issue, in particular in terms of geometric change, but also just understanding appearance change, and not only from day and night, but from seasons. And Michael talked about this a lot, and it's certainly still a problem also for us. What I want to just mention as well, because Michael mentioned 10 postdoc headcount, there's often intern opportunities or research collaborations that we'd like to do. So if you're interested in our training data or these 180 million phone captures or the 10 years of Street View, there's plenty of interesting things to do. And there's a lot of infrastructure built that can support you with simulation, with training data export. So if you're interested in this topic, then please reach out, and we would be super happy to have you and work with us. So with that, we can take some questions.
Thanks a lot, Lynen, for your very impressive work. It's very nice to see how you build your group build this very huge VPS pipeline based on the huge amount of data from Google. And I think now we have some time for questions. And I will start with one for now. And later we will see what question we will have from Zoom and from YouTube. So you show results from both indoor and outdoor, like indoor in the, let's say, Tokyo subway station, and outdoor like the Street View. So do you have some pipelines to implement the transition between outdoor to indoor or vice versa? If so, how would you how are you doing it?
Yeah, so it might be a little boring, but we are running the same thing indoor and outdoor. So indoor is more challenging in many ways because it's more easy to find repetitive structure or homogeneous surfaces, so surfaces without texture. I mean, the obvious one is we all get lost indoor, and that has a reason. It's because it's just not visually salient. There are certainly things that you can do, like tune for indoors or specifically adjust parameters. And we know which of our Street View data is indoor and outdoor, so we can certainly switch system behavior depending on if you are matching against the model that's indoor and outdoor. But there is not a lot of stuff happening here. It's pretty much just engineering. So sorry, it's not really interesting.
Okay, totally, no problem. I mean, it's, I think it's also expected that I think this thing can just work for now already. And next we will have Torsten on Zoom. So I have a question for you.
Hi, Simon. Thank you very much for the very nice talk and for the advertisement. Very much appreciated. I guess I'll owe you a beer at some point. What I was wondering is what your thoughts are on like map representation. I mean, we've been doing like 3D-based representations for quite a while now. What about just going back to like race instead of like really building 3D structure? Can we do like those image-based, semi-generalized relative poses things? Would this help? Could this help to have map representations that are easier to update when things change or that are more compact?
Yeah, I think it's a good point. Certainly, the update part is interesting, and I think as right now we have the luxury to just recompute everything. Like we're actually recomputing this model like once a month, and it's not a big deal, but it's kind of expensive and it's a little stupid also. I think finding a way to do more incremental updates and also like remove things more efficiently would be nice. I think you can, because we have this kind of like tiling scheme, it's pretty easy for us to swap out things. So we can actually, you know, do partial updates at least of like 150 meters chunks. But it would be interesting to look into, can you really do that more dynamic? Can you fuse in data that is perhaps even periodic? Like, you know, what about a market, the classical example of the weekly market that you want to patch in and patch out. I think the reason we didn't do this so far is mostly because the research is still very nascent. But if there was a better representation, we certainly like to adopt it. And I think with lines, you can see in the privacy localization space that there is quite a lot of investment. And I think that could also eventually come into like the mainstream, you know, you just do it because it's more efficient. For us right now, we're doing these things because they're fast and they are fast to match and load, but this is all engineering reasons, not so much, you know, because it's fundamentally the better representation.
Okay, thanks.
Thanks. I think we still have time for a question. So there's a question from Zoom. And Laurie asks, have you published something on the indoor use of VPS in indoor? And this is first question. The other one is, are you using GPS prior also indoors or place recognition before the local descriptor matching stage?
Yeah, so we always use GPS, and it's also non-technical reason, it's a privacy reason. We don't want to search in large spaces, right? You want to really search only locally because that's like, you know, what is agreeable and understandable for the user. That's also perhaps a difference between industry and academia is we really want to be doing things that the user expects and not anything that's like a global search without GPS. So for indoor as well, we search about a 200-meter radius. And if the GPS is more wrong than this, then the system is not going to work. You could certainly search for kilometers if you wanted to, but it's also a bit of a cost question because you then end up loading a lot of these models and you need to do a lot of matching, and the user might not want to wait for that.
Yeah, thanks for the answer. And we also have a question from YouTube. And the question is, do you merge multiple overlapping sequences whenever possible? If yes, can you talk about the representation of such a graph? And is it multi-sequence relaxation?
Sorry, what was the start of the question?
Sorry, is that do you merge multiple overlapping sequences whenever possible? And then if yes, can you talk about the representation of such a graph? Yeah, I think that's the first part.
Yeah, so I assume you're talking about the sequences for map building, and that's like, it's actually kind of an unordered collection of images at this point. So like in bundle adjustment, things are obviously jointly bundle adjusted as a sequence. But for VPS and the structure for motion we do, it's actually becomes irrelevant. Like we just match everything to everything in a way locally. And then we end up with a pretty dense graph, but this graph does not care too much about sequences anymore. Sure, you have IMU signals between neighboring images, but we do an optimization where we select subparts of each graph, and then we just jointly make a structure for motion model of the data that we care about. We don't index all of Street View just because very old data is not that relevant, it's not that informative. So we have algorithms that select, you know, newer data and data that is representative of the environment. So it's also, you know, unfortunately, a little bit more engineering side where we just like, you know, solve a simple problem that gets the job done.
Great, thanks a lot for your answer, Simon. And I think due to the time limit, we have to move to our next speaker. And thanks again for your impressive talk and your answer. Yep.
Yeah, thanks a lot for having me.
Sure. So it's time for our next speaker. And this will be Alex Kendall. Alex?
Hi,
you hear me?
Hi, yes. Can you hear me?
Yes, great. Yep. So yeah, it is my great pleasure to introduce our next speaker, Alex Kendall. And Alex Kendall is the co-founder and CEO of Wave, a London-based company pioneering AI technology to enable autonomous vehicles to drive in complex environments. Before founding Wave, Alex was a research fellow at Cambridge University, where he earned his PhD in computer vision and robotics. His research has received numerous awards for scientific impact and made significant contributions to the field of computer vision and machine learning. He has been selected on the Royal Academy of Engineering SME Leaders Program and named on the Forbes 30 and 30 Innovators list. It is our great pleasure to have you here, Alex. The floor is yours.
Excellent. Thank you very much for the introduction. And I'm really happy to be speaking here today. When the organizers reached out and asked me to give a talk, I was a little bit perplexed because I've spent a lot of my career really trying to build autonomous robots that can have the embodied intelligence on board to understand their environments for themselves and make their own decisions without needing a high definition map. And of course, joining a workshop that's really talking about the state-of-the-art development in high-definition maps is a little bit contrarian to what we've been building. So what I would like to do today is be a little bit controversial and hopefully start a really constructive debate on why this is important. And in fact, I'm going to argue that high-definition maps are not going to be a core part of the first autonomous vehicle systems that actually are deployed at scale. So if I took the abstract for this workshop off the website, I've just put in, I put an excerpt of that on the screen here. There's a phrase here that says, let me just move this out of the way. Centimeter accurate continuous global localization is a key feature for autonomous driving. Fundamentally, I think this is something I disagree with. And I'm going to present a series of arguments and evidence of what we've been doing to build a system that can really scale autonomous driving to some of the most complex environments without needing centimeter accurate localization. This is not how we drive as humans, and it's not how I think the future of autonomy is going to operate. So as I said, no apologies for the controversy, but I look forward to the debate. Now, when people usually argue against high definition maps, the arguments are usually twofold. Either they're very expensive to build and maintain, we've got an ever-changing world, and creating the high definition maps, labeling them, annotating them, and maintaining them is a huge expense. So why don't we not do it for a cost reason? Or the second reason people say is maybe articulated by this meme, which is, okay, what happens if the high definition map is wrong? Then maybe in that case, our car is going to do something that's silly, like drive into a house or drive off a cliff. Now, while those two arguments have some merit, I mean, ultimately self-driving is such a impactful and important challenge today that I think we can overcome the cost problem if we need to. And then, secondly, a lot of people who work on high definition maps then say, well, about the point of if it's incorrect, well, high definition map, it's just another sensor. It's got its own inherent noise, and we need to appreciate what it does and doesn't know and treat it like a noisy sensor, just like we do with cameras, LiDAR, and all the other sensor inputs. And so, that debate can happen, and I think there are merits to both sides. But the more fundamental reason, I think, why we should be looking to move away from a high definition map and why we should move away from really accurate, precise localization is because of one of scale, is because of one of intelligence. How do we, let's take a step back and think about autonomous driving. How do we get these systems out of very constrained environments like what we've seen in Arizona? We have a very structured road where the sun always shines and you have very clear lanes you should drive in. How do we bring them into cities like London, where we predominantly test in the UK, or other cities around the world that I'm sure many of you either live in or have visited, that have really chaotic and dynamic structures that require a level of intelligence that lets you really coexist with human society and know how to move around in these cities? if you build a system that learns to drive on a crutch, like a high definition map, if you tell it the exact lanes to go in, the exact positions to stop in, fundamentally, you're going to come up with a different solution that is really constrained in how it can be applied. If you think about this as an AI problem, how do you build an agent that can drive around and make its own decisions in the world? For me, it's more the philosophical approach of what principles and values do you bring to autonomy that can really let these systems scale? And so what I'm passionate about and what our team has been working on at Wave is, how do we build a system that scales? How do we build a system that can coexist with society, can make its own decisions, and drive using the intelligence to exist in the dynamic and wonderful worlds that we live in urban cities worldwide? And that's really what I think we're seeing today. Well, the first wave of AI, and I think what we've really seen in the 2010s is AI and end-to-end deep learning completely take over vision and natural language processing. I think now is the right time to start to see these kind of products come onto the market. And I've pulled some examples from, for example, the Skydio autonomous drone, or the Covariant robotic picking arm, or our vehicle here on the road in the UK for autonomous driving. All of these examples just to show that now is the right time to build embodied autonomous agents and put them in the real life physical world. Because fundamentally, autonomous driving is an AI problem. So I know that's a bit of a philosophical argument of why I think it's important we build systems that can reason about the environments for themselves. But now let's dig a layer deeper, and I'm going to present to you a framework of a system that can really solve autonomous driving without an HD map. So the first question you might ask is, how do you navigate? How do you move around the world? Well, how do you do that as a human? I think what we do when we think about going to do something in the world, whether it's picking up my water bottle and taking a drink, or whether it's moving around in spaces, we very much work in a topological manner. If you think about the way the place cells fire in our brain, or the way we connect different sequences of actions together, it's very much topological, it's semantic, it's hierarchical. And I would argue that that's exactly what we need to build in our autonomous agents. We need to build systems that are goal conditioned, that have memory. And an example of that, and how I would see an autonomous vehicle acting throughout the world, is that you might say, take the next left turn, or take the next right. When you drive, you don't say, in 5.68 meters, you should make a left turn with a radius of curvature of 15 meters. This is not the way that we drive around. What we do is we understand the context of our scene. We take the next left. Or for example, if you're trying to take a park and drop someone off in a ride-hailing setting, if you give the agent the instruction to find a car park, it can go and do so in a natural way where it fits into the context. Maybe it's appropriate to double park. Maybe you need to find a parking bay. If you have a high definition map that tells you a specific spot to park in, what happens if there's someone else parked there, or if there's people in the way, or there's roadworks, or other things that come up? I think it's very important to be able to move around the world in a way that ties together the navigation with the semantic context of the scene. And the way to do that is with goal conditioning. So moving away from explicit motion parameterization and movement and driving on these invisible railway tracks that high definition maps, I guess, incentivize and force us to do as autonomous driving engineers, but moving to goal conditioning is the way forward. Now, of course, if you've driven somewhere twice before, you should learn and adapt. And so I think memory will play an important part. If you go through an environment multiple times, you should, of course, be able to be better at driving the second time. But I think memory is very much a second order optimization for autonomous vehicles, and something that will come in future generations. But the initial products that get out there, I think with a basic sat-nav navigation system and goal conditioning, will allow us to build autonomous vehicles that can really scale. So this lets us build intelligent agents that can both make decisions that are goal-driven and can achieve an outcome, but also that are aware of their context and their surroundings and make their own decisions for themselves. So what does this look like? Well, for us, we've built a system that takes in all of these as inputs into one giant neural network. We take in the sensory input of the world around us, a basic GPS and sat-nav system, and other things like the vehicle state, and feed it into a single giant neural network to the output, which is controlling the vehicle with a motion plan, which we can verify and make sure is safe. And by putting a single neural network on this lets us really use data to scale the system and use all of the tricks that we've developed in our field around self-supervision, uncertainty estimation, and ultimately computer vision to build representations that can really scale. And so we can pull out representations that let us verify the motion plan, that let us quantify the uncertainty, and ultimately make sure that the motion plan that we're delivering is one that is safe and acceptable. So I've given a bit of a whirlwind introduction to how we might be able to scale autonomy. Now I'm going to show you what we've actually done to build this. So we started Wave in 2017 with this promise of building scalable autonomy, really aiming to build an autonomous driving system that can be first to 100 cities. And so here's the adventure that we've been on since then. The first thing we did, and remember, this is all about building an intelligent system that can exist in the real world and make its own decisions. The first thing we did is we tried to put a reinforcement learning agent on public road or in the physical world on roads. And here what you're going to see is a reinforcement learning system learning to drive from scratch. The system starts off by knowing nothing about the world. It doesn't know what roads are, what lane markings are. It's a neural network initialized from scratch with random weights. And it's driving forward, and every time it goes to the edge of the road, there's an intervention where the safe driver grabs the wheel and it learns from that intervention. And so from those patterns in the data, from the statistics, it's able to learn through, this was a deep deterministic policy gradients algorithm that could learn to feedback and understand, and ultimately what you're going to see in front of your eyes is it learning to lane follow. Now it's going to do so in just 10 episodes of learning. And I think what was exciting here is this in 2017 at the time, we'd only really seen reinforcement learning algorithms that had learned to drive or learned to do things in simulation with tens of millions of episodes. And so to get a system to work, and here you can see it partially learned, it's learned a system that can somewhat feedback and swerve in and out and do a bit of correction, but ultimately ends up running off the edge of the road. But if we keep training it with a few more examples, it's going to ultimately learn to lane follow. And you can see when we turn around this vehicle, here we go, 10 episodes of learning, 10 minutes of experience, and it's learned to lane follow and can do so up and down this road all day long. So what's the next step? Well, of course, I think the key thing here is to really expand this with better representation learning. And so the next step is we set off to improve this with a model-based reinforcement learning. So that previous system was a simple encoder that took the front monocular image, encoded it into a latent space, and learned a policy through DDPG. But what we've built here is a system that could learn to drive through model-based reinforcement learning. We got a lot of these videos of us driving along this road and trained in a supervised setting, trained a dynamics model that could take the encoded states and predict the next state given an action. When we take this dynamics model, we can then use it to learn to drive through imagination. We can take a state and we can then learn a policy and simulate forward with that trained dynamics model how that policy will behave in the world. And you can see in the bottom left some examples of what it looks like when we simulate driving down this quiet country road. And through that, we could train the policy to drive in a model-based setting by taking a reward function and the system that could learn to drive forward. And essentially what this let us do is learn to drive with a lot more robustness. So we could drive in different weather conditions. We could learn from more data. We could really start to scale the system in an offline setting. So we've got a system that can make decisions and it can drive around, but I think what you'll all agree is this is on a quiet country road. It's a very simplistic environment. The next step in building the system is for us to really take it to public roads to drive in traffic. And that's exactly what we did next, bringing in some computer vision and representations that really let us learn and understand the semantics, motion, and geometry of very busy urban scenes. And so what I'm showing here is actually this was some work from my PhD with Yaron Gao and Roberto Cipolla at Cambridge on understanding the world around us from a monocular camera. So this is a supervised learning approach that lets us build a single multitask neural network that can understand the semantics, the geometry, and in this case, instance segmentation of a scene. And this was a single neural network trained, and the contribution of this paper, if you're interested in reading it, was how to use uncertainty to guide the curriculum of learning these multiple tasks in one setting, how to use uncertainty to essentially get the system to focus on the more informative examples for it to learn. And I think this is a really important contribution when it comes to leveraging uncertainty and other self-supervised signals to be able to learn from really large-scale data and extract the right learning signals. So what have we got so far? So I shared how we can learn to drive very efficiently in a model-free setting with reinforcement learning. We can use model-based reinforcement learning to learn in a more robust setting. And now we can scale up the representation with computer vision. The next thing, though, is we've got semantics and geometry from that representation, but now we need to learn dynamics. How do we learn to predict the future? And I'd like to just introduce this with a motivating example. I don't know if anyone would like to guess, but this example image I'm putting in front of you here, is this white car on our left, is it pulling out in front of us, or is it stationary on the side of the road? It's really hard to know from a single image. And so I think what should be clear and what we've seen in the field of computer vision recently is that motion is starting, well, we're now starting to build more and more deep learning models that can reason over motion. And you can see from a video, it's now clear that this car is actually yielding to us. And so I guess, while this does make it clear that the future is uncertain, probabilistic, and multimodal, as we get more information and more context, we can start to have a stronger belief about the future. And so what I'd like to do is share a paper. This is actually being presented this week at ICCV as an oral presentation, and was put together by a fantastic team with the authors on the side here. So I'm really, really proud to share a lot of their hard work. But I think the point that we'd like to make with this contribution is really that the next step to build this embodied autonomous agent that can interact with the world is to understand the future and be able to predict and understand motion. And what you're seeing here is an example on, this is from the New Scenes data set of the ego car driving through a very complex urban scene. And you can see at the bottom left, us predicting the future of how all the different agents in this driving scene are going to react. And on the bottom right, a probabilistic, and you can see during these intersections, a multimodal distribution of futures. This is really important when you're driving in urban environments. So what does this model look like? Well, we call this model fiery, and essentially it takes multiple time steps of input features and lifts them to 3D with an orthographic transform. And we then collapse that 3D representation into a bird's eye projection. So a 2D top-down feature space that's an orthographic projection. So Euclidean space is homogeneous throughout this bird's eye view. We then take this as our state vector, this list of previous bird's eye view states, and we concatenate it with the actions that the vehicle was taking. We pass this to a temporal model. Now you could try to use autoregressive models, RNNs, CNNs, choose your transformer, choose your favorite one. I think we used a convolutional autoregressive model in this paper. But then this gives you a state. Now what you can do with a state is you can then pass the state through another neural network to form a latent representation, which can represent the present distribution. So this is the distribution of futures you expect conditioned on the present and the past. So everything you've seen up to this time step. Now, of course, at training time, we have access to the privileged information from the future. So we can take a state representation that sees the future because, of course, from our log data, we have access to the training time. And we can again encode the future data. And this actually tells us the distribution and where in the distribution that future example was. And now we can train these two distributions to align. And so this means that with a KL divergence matrix between these futures, it means that we can train our present distribution to match our future distribution. But the key difference here between simply trying to regress the future that we saw is that that future is one of many futures. And how does our model know which future to regress without having seen that data? So by learning this distribution, it means we can learn to match the shape of the future distribution, but then we can sample in a way that allows us to train and regress the specific future itself. And so it lets us deal with the inherent uncertainty of the future, but do so in a way that lets us model that distribution, but use the example of the future, the mode that was actually observed, as explicit supervised training data. And so then, of course, we can take that sample and unroll it into the future and train to regress future outputs, whether they're semantics, motion, geometry, action, whatever you're interested in predicting. And so in our case, it's really about understanding the scene and controlling the vehicle. Now, just to show you some results of why all of these contributions are really important to bring forward into this future prediction system is firstly, bringing in temporal context is really important. We saw a big uplift in performance there. Transforming to 3D gives us another uplift in performance. Being able to unroll into the future on a per step basis but I guess most significantly was moving to a probabilistic model that really gives us this this performance of future prediction. This is measuring the future video panoptic quality, essentially the quality of the semantic and instance segmentation into the future. So to show you some quick results, when you put this together and train it on, in this case, the NewSense dataset, you get these results. And so you can see here in the bottom right, this is clearly demonstrating multimodal future prediction around a unprotected right turn scenario. Here's another one where you can see we can predict the multimodality of a vehicle that initially is uncertain and then makes a U-turn in the intersection in front of us. So you can really start to learn multimodal futures in a way that's quite robust from, and remember this is from monocular images. And then here's another one overtaking some parked vehicles, and you can see that it can reason about these kind of maneuvers, which requires a lot of, I mean, one of the nice things in this model is it can jointly reason about the scene context and the other vehicles. We don't produce a state vector for each vehicle explicitly, but it's a dense, latent bird's eye view feature space, and we can, the neural network can learn from the information that's both on the information that's both from the scene's context, I guess the wider semantics of the scene, as well as each individual agent in the scenario. So I thought it was important to share that work, and if you want to learn more, please do attend the oral presentation that Anthony Hu will be giving later this week at ICCV. Right, well, so I've shown you all the key ingredients, you know, a model-based reinforcement learning system, a computer vision representation, an ability to reason over dynamics and predict the future. What happens when you bring this together into this one big neural network and give it this goal conditioning that we spoke about? Well, here's a video of the results. You can see us, this is our vehicle driving in London, driving on some very busy, unstructured roads, driving on roads it's never seen before. So it has no high definition map telling it where to drive, or it's not following invisible railway tracks. It's not being told where the traffic lights are or where it should be stopping at various intersections. It's interpreting that all in real time based on these ideas and understanding environment for itself. And you can see here it's able to drive you know, fairly robustly in some quite unstructured environments. I mean, even here it's very unclear, you know, where particular lanes are. You've got bus lanes, vehicles that you need to pass and overtake, bike lanes that are sort of intersecting with the driving lanes. So the point is it's a very chaotic and unstructured environment. This is what we test in, day out in central London. And with this, we've been able to put together a system that can learn to drive in this level of complexity. And here's a fun example from a few weeks ago that I just thought I'd bring up for this talk. This is not one we've shared publicly before, but I thought it's a really interesting example to show. Here you can see our vehicle coming into this very, very tight space and making a left turn. And this is on a road it definitely has never seen before during training, but I just wanted to show it because the dexterity that we're able to learn and the ability to really reason about context is so important. If you look at this road, it's actually too skinny for our vehicle to fit down the road itself, and it's had to pop its left two wheels on the side of the footpath on the left to be able to squeeze down. And this is something that human drivers will do all the time. But to see this you know, embodied AI system actually drive down this environment and with this kind of level of reasoning, I mean, this is what it's going to take to have these kind of systems intelligently operate within cities around the world. And so, you know, I was able to successfully drive down the space. And here's a very, very tight gap with a van parked on the side. And so you can see and this is all driving with monocular cameras. So no range sensing. I mean, well, everyone in computer vision knows as well as we do how good monocular depth estimation is these days, but you can see it drives out and it makes a turn. And yeah, I think the passengers there were fairly happy. Right, so I've made a bunch of claims that we can drive and really build a system that can scale, and one that we believe can be the first to 100 cities for autonomous driving. But what I'm now excited to share is I guess, not just the fact that this is theory, but we've actually run some experiments that show that this is possible. So we trained the system, the one I just showed you driving, purely on London training data alone, and have now taken it to many different cities in the UK. So here's some examples here. We went to Liverpool, Manchester, Leeds, Coventry, Cambridge. And these cities, we drove in them in what we call a zero shot test. So it's never seen data from these cities before. Now, this surprised me. I thought we'd have to get a little bit of training data to do some domain adaptation, because the driving environments are quite distinct in these different cities. You've got the cobbled streets of Cambridge, or going around the football stadiums in Manchester with a lot of football fans around. I mean, there's different driving environments. But our system was able to drive in all of these different environments just from the London training data alone, and using a basic sat-nav system to help it navigate around. So this is really, for me, evidence why I think we can drive and we can really scale our system without an HD map. You might ask, what will it take to go to somewhere like, I don't know, Amsterdam or Paris or Munich, or somewhere in the outside Europe and the rest of the world where you have to drive on the other side of the road, on the right-hand side of the road, unlike the left-hand side where we drive in the UK. And there, I think we will need a little bit of extra training data to adapt to that domain. But I think it will be monotonically decreasing amounts of data with each new domain we go to, because the more data we get, the more coverage of the driving state space we will have. And of course, we know how good domain adaptation is. The sort of general representations we learn of the dynamics that we drive in the world, I think will be fairly common across all of these domains. It's just some specific behaviors that will likely need adaptation to. So I really do think this is the way to scale autonomous driving globally, is using this learning loop of data and a deep learning network that's flexible enough to learn a representation to drive globally. And we can do this without an HD map. Just in case you do think that all of these driving environments are fairly similar, here you can see I just pulled out some spider plots that show across some of the different driving domain features, whether it's presence of cyclists, how many traffic lights there are, different turns. If you look at all of them, so this is comparing them all to London, which is in red, you can see that the Cambridge in top left in blue, or Liverpool in green in the bottom left, or Manchester in blue in the bottom right. You can see all of these domains actually have fairly different statistics within the driving environments that we drove in these cities. So I just wanted to show this data in case anyone thought that all UK cities are the same in terms of driving environment. I mean, they all have their unique challenges. They all have different and unstructured roads, different vehicle behaviors and pedestrian behaviors. And we observed that in the testing that we did. We drove for 1,000 or so kilometers in each new city we went to. Great. So where to from here? Well, we're really excited to, having announced in the last couple of weeks that we've partnered with some of the largest fleets here in the UK to now actually take this technology into actually deploy it with some commercial partners in last mile delivery. And so we're going to be working with Ocado and Asda, who are two of the largest supermarket retailers here in the UK, and they're fantastic partners for us to actually trial the system in production. And so this is not just a science experiment, but I wanted to make the point that not only have we been able to build a system that can drive without an HD map, that has the intelligence on board to really understand new environments, but next year we're going to see this piloted in London with safety operators, but essentially getting the experience and getting more data to continue to learn and improve the performance of the system in commercial last mile grocery delivery, which is a really exciting moment for us as a team. And ultimately what this means is it's producing this learning loop where we're able to get very large scale data and pass it into this model that can predict, that can understand and can control an autonomous vehicle at scale based on what it sees with vision. And we see this as a sort of centralized driving intelligence that can operate across different domains, whether that's different vehicles, different cities, or different use cases. All of these are just different distributions of data, and we should have a system that has the flexibility and the intelligence to learn to operate across all of them. For me, this is really what's going to take autonomous driving globally within the world. And we feed a lot of data into this learning loop. We have synthetic data that we generate from procedural and virtual world simulation techniques. We have off-policy data. So some of the fleets that we're partnered with are some of the largest in the UK, and we deploy our camera sensors on them with a small amount of compute in a 4G chip and essentially send back data from very large-scale fleet deployments to the cloud, which allows us to learn at scale. And then, of course, our actual vehicles that are testing on the road collect on-policy data, where we collect interventions that let us learn to overcome them and to not make these mistakes again. So bringing together all these sources of data, putting it in one giant learning loop, and then deploying this on the road and seeing commercial deployments next year, I think this is the kind of learning loop that's going to produce a system that can really scale. It can deal with the complexities of London, which I think are some of the most complex, environment I think we've seen autonomous driving deployed in anywhere in the world. Not only can it work in a complex environment, but it can scale effortlessly to new cities. And so for me, what I'm really excited to share with you all, and I've loved being around the ICCV community since I first went to 2015 in Chile, at ICCV in Chile, in Santiago in Chile. That was an amazing meeting where we were first starting to see some of the results of some of these scene understanding and computer vision algorithms, through to where we are today, to having a system that can drive on the road, understand its environment, and learn from data at scale, ready to be put into commercial pilots next year. I think this has been a really exciting journey. And so just to, just to conclude, if this is a vision that you share, do please get in touch, because I think we're a team that's really excited to build this, and it's really just the beginning. There are so many interesting problems to be solved here. How to build a more robust system, how to use self-supervision to really extract the right data from these data sources, and build a curriculum that can robustly solve these things at scale. But I would welcome any questions and happy to have a debate about this, but I hope you've enjoyed this contrarian view about how we can build a system that can learn to drive without an HD map and what it looks like on the roads. So thank you very much for listening, and happy to take any questions.
Thanks a lot, Alex, for very impressive work and very impressive results you showed on a very different approach as previous work, like you use this goal condition or goal triggered approach to solve autonomous driving. I think now we have some time for questions, and I will start with one. So when do you expect that we will have autonomous vehicles at scale on the road without using HD maps?
Yeah, so
3 to 5 years.
Yeah, these kind of questions about timeline, I think it's always important to quantify them. So what we're going to see is next year we will be starting commercial pilots, seeing our technology driving in customer operations, delivering groceries in London and other areas of the UK. This will give us data, and I think we'll start to see the scale very quickly over the next few years to multiple cities. I think as we collect 1 million hours, 10 million hours of data, this will give us enough to really train a performant driving system, and one that can be validated and put a safety case together. And when you have that together, it's really a matter of horizontally rolling it out. It's one that can adapt very quickly to new cities, and that's where I think we'll be incredibly quickly growing to hundreds of cities, hundreds of fleets, and we'll see a global solution in place. But this is a generational problem. It's not going to happen overnight. It won't be there by next year. But I think over the next decade or so, we're going to see autonomy completely transform the way that we move people and goods around cities.
Great, thanks for your answer. I'm very looking forward to the day that everybody will have an autonomous driving car. So yeah, we also have a question from Zoom. So it's from Andre. The question is, with the approach you are proposing, is there a concern about the explainability of the driving decisions? Because, for example, it's not explicitly detecting pedestrians, stop signs, etc. And the question is that I think it's mainly about the explainability of the approach you propose.
Yeah, let me just put this video and play this video in the background as I answer these questions. But what you see, I think this is I mean, I've always been a criticism of end-to-end learning approaches, right? They're a black box, or you can't understand why they're making the decisions they make. But fundamentally, this is the way that we're seeing intelligent systems developed. There are a few things I could point out, like, I don't know, I think it's very polarizing, but there is some merit to some of the systems around causal reasoning or saliency analysis of models that let you understand the statistics of what it's doing. Or, for example, in my own PhD, I did some work on quantifying the uncertainty of models and understanding when you're out of distribution or within training distribution, and can you quantify what you don't know. And so I think these kind of approaches are making a lot of progress. And what I would say is that when I started off in the field of computer vision as a researcher, it was really important just to chase benchmarks and improve performance. But I think today, we're seeing ImageNet, Cityscapes, many other computer vision benchmarks almost solved through supervised learning. And now it's really interesting to say, okay, can we understand how it's solved? Why do they make the decisions? What are the edge cases? Can we do it with self-supervision? So I think that this is something that we're making huge progress on as a field, and is one that I think will not be a bottleneck to not hold back this technology being scaled. But fundamentally, the way that we build a safety case for autonomous driving is one around statistical validation of the end-to-end performance. This is the way that many of the other more classical approaches you see deployed on the streets today also validate the system. And the same we can do here. We can test over many miles of data and essentially validate the performance is correct in an end-to-end fashion. And so it doesn't stop any of the safety verification, but from an engineering development perspective, our ability to understand failure modes, analyze the data, look at the manifolds produced, all these kind of things. I mean, there's open research questions, but also a space that is seeing huge progress in the last few years.
Thanks a lot for your answer. And sorry, we also have a question from YouTube. So the question is that in a very structural scenario like urban roads, how can the agent learn some rules beforehand without a HD map? For example, like there's a cross, but the vehicle can only turn left. I guess the question is that how do you make the agent to learn something like traffic rules beforehand without a map?
Yeah, I mean, look, let me go back to this example. If you look at the video just here, you can see our car stopped at this red light. And then when the light turns green, we're going to pull ahead and move forward. Now, we never told our system either A, what a traffic light is, or B, it should stop at red lights and go at green lights. This just came from the prevailing patterns in the data. So when you take expert data and you train our system to drive based on that data, this is an overwhelming pattern that you've seen. But of course, there are many edge cases where that's not true, right? So if you put together these rules that often become brittle at scale, you're going to struggle with some edge cases, but our ability to pick out these things from patterns in the data alone is what really makes the system special. So the fact of the matter is, do you think it's possible to write down the rules of the road in lines of code or in a rule book? I mean, even the highway code, or I don't know which countries everyone's from, but whatever the government puts out for the rules of the road, I don't think that how they're written down it's necessary, but not sufficient to be able to drive on public roads. I think you really need to understand driving cultures, especially to be performant and accepted within society. And so for us, the best way to do that is let the data speak for itself and really train the system through experience.
Yeah, thanks a lot. I think it's very impressive to see how the video that you showed here that the agent can just learn these rules, let's say from end-to-end network without explicitly tell it what to do. It's very, very impressive. Okay, I think due to the time limitation, we have to conclude our first section for the workshop. And what I would like to thank again for all the speakers we have for the first session, and also thanks a lot for all the audience to join our session, either from Zoom or from YouTube. And our workshop will continue in around 30 minutes, which will be 5:40 p.m. EST or 11:40 a.m. EDT. So see you everyone in 30 minutes, and bye-bye.
Thank you.
Thank you, Alex.
All right. Hello, everyone, and welcome back to the second half of our workshop on map-based localization for autonomous driving. My name is Patrick Wenzel, and it's my great pleasure to chair the second half of the session. The schedule for the second half of the workshop is as follows. First, I will give a short introduction of our relocalization challenge. Afterwards, we will have talks from the winner and the second place of our challenge. Finally, this session also hosts 3 invited keynote talks from Felix Heide, Torsten Sattler, and Wolfram Burgard. Our relocalization challenge is based on the Artisans and TUM 4 Seasons dataset, which covers a vast variety of conditional, seasonal, and structural changes throughout the year. It covers 9 different scenarios recorded in and around the city of Munich in Germany. For the challenge, we selected 3 different scenarios for benchmarking, namely neighborhood, countryside, and old town. We do provide $1,000 for the first place of the challenge and $500 for the second place. Therefore, this is only possible due to our workshop sponsors. So I hereby would like to thank Artisans and Kudan for sponsoring this event. As mentioned before, the data for the challenge is based on the 4 Seasons dataset. And for each scenario, we provide 1 reference map with 6 degrees of freedom reference pose information. Moreover, for each reference map, we provide a query map for which the task is to estimate the relative 6 degrees of freedom poses between the reference and the query frames. Finally, we evaluate the performance of the relative pose estimates. For the challenge, we've selected 3 different scenarios. And the scenarios are recorded in different areas of the city. So the first scene is captured in a local neighborhood covering a residential area. And the second scene was captured outside the city in the countryside with fields next to the streets, which covers very homogeneous and repetitive structures. The last scene was captured inside the old town of Munich, covering many dynamic objects such as cars and pedestrians. In this slide, we show sample images taken from different recordings for each scene. For example, in the neighboring scene, one can see drastic structural changes over time. So you can see a house which was built upon during the time of recording, which shows drastic structural changes within the data set. And in the countryside scene, one can nicely see the repetitive structures and seasonal changes, including snow. The old town scene shows dynamic objects such as cars and pedestrians and covers day and night changes. And for the challenge, we provide always a pair for each scenario. The winner of our challenge is a team from MACV3D, and the title of their winning submission is MacLoc, a robust and accurate visual localization pipeline. The second place of our challenge is a team from Oppo Research. The title of their submission is Visual Localization with RLocs and Sequential Localizer. I will now play back their talks.
Hello everyone, it's an honor to share our localization method. We will introduce a visual localization pipeline called MacLoc, used to obtain robust and accurate 6 degrees of freedom pose estimation under challenging conditions, and various 3 scenarios include indoor and outdoor scenes. Different times across the day, different seasons across the year, even across many years. Our method can be divided into 2 stages, mapping and localization. We will elaborate on those 2 stages respectively below. First is mapping. Mapping includes 5 steps: image processing, feature extraction, mapping, space reconstruction, and map refine. In image processing step, each image will reset to make the largest dimension, 1600 pixels, while retain its origin and aspect ratio. Some pixels of bottom right border may be cropped to extreme dimension is a multiple of 8. Since the bottom part of the camera view was always occupied by the car shell, a local feature in that area will impede subsequent feature matching and triangulation. We remove the local feature in that area by masking. In feature extraction step, superpoint was selected as our local feature extractor. The non-maximum suppressing radius and key points threshold is turned based on the experiment calculated in CVPR 2019 image matching challenge. As a result, about 1,500 key points was extracted for each image on average. The matching step produced Sparrow's 2-degree key point correspondence between two images that share some view areas. Those correspondences are the key to recover 3-degree map point position by triangulation. Image retrieval before we found Sparrow's correspondence by local feature matching. Database image was retrieved to obtain the top key nearest image pairs, between which a large number of local correspondences can be established. There are two ways to find the image level correspondence by local feature similarity or characteristics of the current sequence. Sparrow's correspondence superglue was implanted for local feature and matching. After we obtain a local correspondence, correspose was eliminated, and those correspondence complete with polar gradient was eliminated. Sparrow's reconstruction by triangulation step, we use CoreMap 2 box to reconstruct the maps sparsely. Global bundle adjustment was performed once, only to save the computations. In full season, this site, the car always travels forward. The baseline in XY direction of camera coordinate system is relatively narrow, which causes the triangulate map point suffering from a large uncertainty in Z direction. So we formulate the uncertainty of map point like this. For each observation we solved for this Jacobi, it responds the relationship between 2-degree pixel and map point. For this, we can get the information matrix of one observation. After accumulation, we can get the total uncertainty. The uncertainty of orthogonal directions can be calculated by eigen-decomposition. And those map points with large uncertainty can be removed from the map by setting a threshold. The value of threshold should be influenced by many factors, such as the scale of reconstruction scene, the number of mapping images, resolution of per images. The figure shows the effect of pose refine. Next step is localization. Localization constant of 5 steps. Image processing, pre-processing, feature extraction, matching pose estimation by rig perspective endpoints and pose refine. The first three steps are same as below. We also use superglue to find local reconspectance, global feature similarities between QN image and database image or mapping image were evaluated by consign function, and the top k nearest pairs were retrieved. Corey images were also sequential, and we also utilized this parameter to retrieve more image pairs. I won't elaborate here. Pose estimation by rig perceptive endpoints step. The full season dataset was recorded by a stereo camera with given extrinsic parameters. During the pose estimation step, we retrieve the image captured at the same step as a whole, and only saw the pose of left camera. We figure out this strategy advance actuaries and robustness. So once all the pose of Corey image was estimated, we found some of them localized unsuccessfully. For that, we further considered the temporal characteristics of Corey images. We first assumed that must exceed some co-visible paths between consecutive images, and some local correspondence can be established among the sequence Q images. While we fixed the camera pose of all mapping images and involve those Corey to Corey correspondence into map by triangulation. At last, we ran the global optimization on camera pose of all Corey images. At last, in January, the dataset is different from other datasets about visual localization. First, it's designed for autonomous driving. The urban road sense is very different from the indoor. It has lots of dynamic objects such as people and cars, and across the seasons, that makes feature extraction and matching more difficult. So we expect better feature extractor and matcher to cover it. In addition, the direction of travel of car makes the triangulation worse. So we can use more cameras and wider baselines to develop accuracy of map point. That's all. Thank you.
So I would like to thank the authors from the winning submission again. And unfortunately, they cannot be here today, but I'm pretty sure if you have questions from the audience, feel free to ask them and we will forward them to the authors. I will now continue with the second winner.
Hi everyone, my name is Yuchen Yang. I'm an algorithm engineer from Oppo Research Institute. Today it's my pleasure to introduce our visual localization with RLOX and sequential localizer, which has won the second place in ICCV 2021 challenge of map-based localization for autonomous driving. I'm very thankful to my collaborators, Jiafei Xu, Xu Dongzhang, Shuanggao, Kunjiang, Jijun Li, and Yan Dongguo. This is the overall pipeline of our approach. Our approach includes two parts. The first one is RLOX, which was introduced in ICI 2021. The second part is sequential localizer. RLOX is a visual mapping and localization system. It can reconstruct sparse point cloud map from database images. Also, it is able to localize query image using deep learning features, semantic segmentation, and PMP plus RenSec. Sequential localizer combines SLAM and visual localization from RLOX to achieve robust pose estimation. It uses SLAM to get relative poses of query image sequences and help image retrieval. Database extension is an approach which uses well-localized query images to triangulate more point clouds and increase robustness and accuracy of visual localization. After that, a loose coupling combines the results of visual localization and SLAM to get the final poses of query images. Here is the pipeline of RLOX. It contains 4 parts: mapping, image retrieval, initial pose estimation, and post-iterative optimization. Mapping builds semantic point clouds from database image set. Image retrieval model retrieves database images which are similar with query images. Initial pose estimation uses features in query image and point clouds in database images to estimate a coarse camera pose of the query image. Post-iterative optimization optimizes the camera pose by observation constraints filter. In this challenge, mapping, image retrieval, and initial pose estimation is used. Deep learning models used in these 3 parts are different with RLOX. This is the mapping part of RLOX. It uses database images, camera poses to reconstruct a sparse semantic point cloud map. We extract zero point and NetVRED from database images as local features and global features. BizNet V2 pre-trained model on cityscape is used to get semantic labels of each pixel of database image. Since 4 seasons dataset is very similar with cityscape, this model performs well on 4 seasons dataset as well. NetVRED can get similar image pairs and local features from similar images is matched. Here we use N matching and geometric constraint to acquire matches between images. After feature matching, we use CallMap SFM to reconstruct semantic point cloud according to given camera poses. Finally, we get a sparse semantic point cloud map. This is localization part of RLOX. It uses point cloud map to estimate camera pose of query images. Similar with mapping, we extract zero point and semantic labels of query images. Here, HOW image retrieval is utilized to get similar database images. We match nearest neighbor features with query image and top case similar database images. Since nearest neighbor matching contains lots of mismatches, also matches on dynamic objects should not be used in PMP. So we check semantic labels of matched features and point clouds. Then we remove matches whose semantic labels are different or belong to a dynamic object. Here we can see that the mismatch and features on vehicles are removed. After that, PMP plus RenSec estimate k possible poses from k database images. dbScan is used to cluster inline poses. Matches from these poses is merged and do another PMP plus RenSec to get the final camera pose. RLOX is able to achieve robust localization in conditions like cities or towns. These scenes have rich feature point and easy for image retrieval and feature matching. However, unlocks cannot solve things where image retrieval and local feature doesn't work. For example, if weather of database and query image is very different, local features doesn't work, especially in scenes which has lots of vegetation. A summer image can be completely different from a snowy day image. Also, if dataset has similar but different scenes, it is also difficult to obtain a correct database image by image retrieval. To solve the problem, we add sequential localizer. As we have introduced before, sequential localizer utilizes SLAM to estimate relative camera pose and combine it with visual localization result from unlocks. Relative camera poses of query images helps filtering out incorrect image retrievals from unlocks, which increase accuracy of one-frame localization. Here, database extension use query camera poses and matches to triangulate more point clouds. Then, failed cases in unlocks is localized again by point cloud from database extension. Finally, a loose coupling combines SLAM result and visual localization, then output the final pose. Image retrieval, filter, database extension, and loose coupling are three main parts of sequential localizer and will be discussed in the following slides. The first part of sequential localizer is image retrieval filter. This part uses unlocks result of last frame and SLAM result to optimize image retrieval. If last query image is successfully localized, we use SLAM relative pose to predict current pose. Then we compare distance and camera normal angle between prediction pose and database cameras. After that, we get the filtered retrieval results. This approach can help solving similar scene and incorrect retrieval problem. The second part of sequential localizer is called database extension. This part uses well-localized cameras to help localizing other cameras. But how to judge whether a query image is well-localized or not? Here we use Monte Carlo sampling to randomly sample 50% of the matches and do PMP plus ransack again. Then we get a subpose. If a query image's localization result is correct, the matches should be regular. Then sampled matches should also be regular and reproduce similar camera poses after PMP plus ransack. So we compare distance between camera pose from unlocks, and if the distance is too large, this camera pose should not be very accurate. Then we use accurate camera poses to build a map again and localize failed cases in this map. Finally, some of the failed cases in unlocks can be solved. The third part of sequential localizer is the loose coupling. It combines SLAM results and visual localization result. Here we use ORV SLAM 2 to get the SLAM result of the query images. It is known that SLAM result is smooth and robust for a short period, but has global drift, especially in countryside cases, which has very few cases and difficult to do a loop closure optimization. Visual localization is opposite to SLAM. The relative pose can be coarse, but it has no global drift. Loose coupling find failed cases in visual localization and find closest success frame. Then we interpolate from success frame to failed cases by SLAM result. Finally, we get the final pose of all query images. This page shows the result of our approach on 4 seasons dataset. We can see that our logs has several failed cases. After adding sequential localizer, all of the failed cases is solved. This is the results of neighborhood and old town. These two sequences has much more features. RLogs plus sequential localizer can also achieve accurate and robust localization. Finally, let's make a summary and outlook. The advantage of our method is that we use simple localization pipeline and SLAM. Our mapping and localization pipeline is similar with some open source approaches such as hlog and capture, but not exactly the same. Also, we proposed sequential localizer, which uses SLAM to improve image retrieval and visual localization. The limitations of our method is that it's not very efficient and it cannot run online. As for the future work, we firstly would like to solve the limitations above and make a tightly coupled SLAM and visual localization system, or a map-based SLAM. Also, we want to integrate more sensors such as GPS in outdoor environments and Wi-Fi or Bluetooth localization in indoor environments. That's all for my presentation. Thank you. If you have any questions, feel free to contact me.
So I would like to thank the speaker for the interesting talk and for, again, congrats for winning the second place of our challenge. We would now have time for any questions regarding the talk. I can start with one question. So what I'm interested in is whether you evaluated the difference between using and not using semantic labels for outlier removal, what you've proposed in your talk.
Thank you for inviting me to this talk. It's a great pleasure. And the problem is that, well, we have not tested on 4-season dataset, but we have tested on other similar dataset such as CMU seasons. And we found that using semantic labels did make a big difference. I think it's very important for season changes, I think.
Okay, thanks a lot for clarifying. I have maybe another kind of related question to that. And did you also try to leverage the semantic information for the image retrieval step?
No, actually. But in some cases, we can use feature matching number of in-R feature matches to re-rank the image retrieval result to make the retrieval more accurate and remove some incorrect image retrieval.
Okay, thanks a lot. I think we don't have any more questions. So I would like to thank you again for joining and for providing these answers. Thanks a lot.
Thank you.
Then we would now continue with our first invited keynote talk for the second half of the session. It's my great pleasure to introduce our next speaker of the workshop, who will be Felix Heide. Felix Heide is a professor at Princeton University, where he leads the Princeton Computational Imaging Lab since 2020. He is also a co-founder of Algolux, where he heads research and development of full autonomous driving stack. Felix received his PhD from the University of British Columbia and was a postdoc at Stanford University. His doctoral dissertation won the Allard Fournier PhD Dissertation Award and the SIGGRAPH Outstanding Doctoral Dissertation Award. His research explores imaging and computer vision approaches, including harsh environmental conditions, imaging at ultra-fast or slow timescales, freezing light in motion, and imaging at extreme scene scales. It's a great pleasure to have you here today, and I will play back now the recording of his talk.
All right, thank you so much for having me. I'm really delighted to give today's talk about designing cameras in an end-to-end fashion to detect what I call the invisible. That is imaging and computer vision in harsh conditions. So today's imaging and vision systems surround us in our daily lives. We use these in our personal devices, in health and robotics, and in our self-driving vehicles of today or of the future. But to build really robust vision systems, we must handle edge cases. Edge cases can not only be the edge cases such as classes that are really seen, but for example, also weather conditions, as shown here, dense fog, where I'm showing you a histogram or a capture campaign done in Northern Europe, where we captured a very small amount of ultra dense fog. And it is challenging to use supervision of existing supervised models to tackle all of those edge cases, just because these cases are very rare and you need a very massive machinery to capture those cases. And also, we want to make sure that we handle those edge cases not only for one specific camera system, where we maybe have the ability to build up a very large system, very large training loop that allows us to capture, re-annotate, have some active learning in there, do that for one particular system, for one camera generation, but also do that for different cameras for diverse applications in the world. So let's have a look at one specific harsh case. And this is a harsh case that doesn't even happen that harshly. That is just nighttime imaging and computer vision. Here you see an example of the captures that today's vision systems and autonomous vehicles have to handle. So in this case here, we have very low contrast around object discontinuities, lots of ambiguity in the scene, but also lots of ambiguity introduced in the ISP, in the post-processing, in the sensing itself due to HDR capture conditions that we have to handle here. So it is not really only the scene that we need to be worried about. It is, in fact, the whole chain, all the way from photons emitted from some source in the scene or the vehicle itself, all the way down to an image or perception output. So here's a typical imaging chain that could be found in a self-driving vehicle, for example, where light enters the scene, is focused through some optics on a sensor, which digitizes the light and gives us a digital reading that we then process in a relatively complicated cascade of individual processing blocks in the so-called image processing pipeline, the ISP. That spits out an RGB image that we can then feed into a downstream neural network to perform object detection, for example. And so, as I said, today, all of the edge cases that happen anywhere in that signal chain can happen in the scene itself, in the optics, in the ISP. All of these edge cases are really handled in the downstream neural network using supervised training. We know that that works. That is a good approach, but it doesn't really solve the problems where they happen. So the best practice is to use supervision to handle the edge cases. And that is not only because that is the most successful approach, but because the downstream neural networks are differentiable. So we can actually add training data that covers those edge cases and then have our model learn to cover those edge cases. The earlier blocks in the signal processing chain, the imaging chain, are not necessarily differentiable. So we have ISPs that are not differentiable, sensor designs that are not differentiable, optics that are not differentiable. The scene itself is also not differentiable. So this makes it challenging. And so we have in practice to manually design those blocks that are essential in an overall vision system. And this is done today by GoldenEye experts. And months and months of hand tuning, for example, if you take the ISPs and their parameters as an example, then those experts design with a lot of domain expertise those blocks, make them perform good with respect to traditional image quality metrics oftentimes, and also sometimes visual inspection. So those blocks are manually designed, and it does not necessarily mean that they're optimal for computer vision applications such as object detection here. And this really goes for all steps in the imaging and vision stack. So in this talk, I'll show an approach how we can take those blocks here, the ISP, for example, make it differentiable, make us, enable us to optimize the weights, the parameters, the processing itself to perform better and to tackle those edge conditions, edge scenarios where they're oftentimes generated, where the ambiguity is oftentimes generated in the earlier layers of the camera pipeline and in the scene itself. And I'm also going to show how we can do that even further down the line in the optics, how we can design customized optics, can really build an end-to-end system that goes all the way from photons in to detection out and optimize the entire camera stack here. And even going one step further, I will show you how we can represent the scene with a differentiable model and then think about completely different new ways how to do object detection and inference, for example, by matching an observation as an optimization problem. So let us first dive into ISPs. So I want to look at a computational camera pipeline that optimizes an ISP for the edge cases. So we can at least rule out the edge cases that are introduced in the ISP itself. So an ISP, as I mentioned before, contains many complicated processing blocks with a large set of discrete and continuous parameters. And these blocks are oftentimes not differentiable. So how do we make it differentiable? This works in two steps. We first learn a differentiable proxy function, an approximation of the underlying ISP that mimics the ISP. So it takes as input raw images, raw sensor readings, and outputs an RGB image. And then we take that proxy network and we fix its weights, and we can then backpropagate gradients from a loss function that may be defined on the image or a downstream neural network all the way back to the parameters, the inputs of that proxy network. So we can solve it as an optimization problem. So let us first look at how we learn this differentiable proxy. So consider a black box function that is our ISP that takes as input raw input images and parameters, the individual ISP block parameters that affect the behavior of the ISP. Then what we do in order to generate a training data set that we can use in order to mimic this ISP is sample the parameter space of input parameters of this black box function. That gives us a training data set of parameters, an input image, and outputs of that black box ISP. It can be a hardware ISP, software ISP, it doesn't matter. Now what we do is we take a relatively standard image-to-image network, a UNet with some minor modifications that takes as input the parameters and the input image itself, and we generate then, we optimize this network to have the behavior that we intend with this particular network, that is to reproduce the behavior of the ISP itself, depending on input image I and a set of parameters P. So now once we're done, finally training our network on this training data set that we generate from the hardware ISP, we freeze the parameters of this particular network, and we keep it then as a function that mimics our ISP. But now the nice thing is this is a differentiable function that we can use to optimize the input parameters. And this is the second stage. So we take this fixed network and it takes input the parameters, the particular raw image that we're interested in, and then we place a loss function on the output of that particular proxy ISP. Let's say, for example, we have a perceptual loss, a loss function that is defined on the output of the ISP, and a reference output, a specific target value that we want to achieve, for example, from simulated data. Then what we can do is we can take that task loss and backpropagate gradients from the task loss through the fixed neural network all the way to the input parameters, find us the optimal parameters that perfectly represent our target image, minimize our target loss function, and solve a black box parameter optimization as a first order optimization problem using existing optimization algorithms, stochastic first order optimization algorithm. So now how do we use this machinery to go further and do joint image processing and detection, for example? So a relatively naive approach is to take a fixed neural network, a downstream neural network, an object detector, for example, faster RCN, and concatenate that with our proxy. And then we have an end-to-end pipeline that itself is differentiable. We can define an IOU loss on the outputs of the object detection network, and now backpropagate the gradients all the way to the input parameters of the ISP. Optimize optimal ISP parameters for that particular IOU loss that we're interested in. We can even go one step further, and we can include the parameters of the object detection network itself in this optimization, slightly change the optimization up so that we can use different learning rates, do some tricks about the learning schedules, but in the end, we can basically optimize for both the ISP parameters, hardware ISP parameters, as well as object detection network weights. And this is an approach that works extremely well. So even on a small data set, just to show some cool qualitative examples, we've been able to outperform state-of-the-art stacks that have been deployed in the wild. For example, here we reproduced object detections on a Tesla autopilot stack that we reverse engineered, and you can see this version of the autopilot stack. Folks were relying quite heavily on radar. There's quite some flickering in there in the detections, and we can do really well even with a relatively small data set and use pseudo raw data input that came from the cameras here. Even though we don't have quite the amount of training data that the Tesla has available, large machinery that's built around it, we have benchmarked against them and achieve substantially higher AOU values on relatively large data sets that we captured and manually annotated. So here's an example, a very different sensor, an AR231, that has a different color filter array under harsh conditions, just mounted randomly behind the windshield. And you can see that handling completely different cameras, different conditions can be done very efficiently with this approach because we train all of the parameters jointly here, all the way from the low-level image processing blocks to the downstream neural network. Here's another example in extremely harsh weather. And here you can see that image processing approaches jointly with downstream detection can certain issues that we have. Multi-sensor setups, for example, LiDAR, which becomes completely unusable because of the heavy backscatter. So just a few examples that show you that this is a successful approach to overcome key challenges in vision systems. So let's go one step further down the chain. So look at how we can optimize optics together with the entire stack, together with the ISP, with the downstream neural network. So today's optics design is done manually by manual optical design tools such as ZMax or Code5. Here you see some of those guys, some of those imaging and optics experts that optimize really elaborate optical systems and can do well in these traditional tools. But key thing here is really that they're optimized in isolation for traditional compartmentalized loss functions and metrics such as spot size, without consideration of a downstream of a network or an application. These modern tools are really awesome in the sense that they have a huge library of individual designs that optics engineer can rely on, different that features different materials, all kinds of different applications for these optics, and they're really easy to use these days. But as mentioned before, one of the big downsides is that we cannot really easily backpropagate gradients through the optics. We cannot design the optics jointly with a computer vision stack. We overcome this by building, again, a proxy model, differentiable modeling of the point spread function here, in this case, especially varying point spread function that we trace here through an optical system, by modeling these PSFs, which describe the optical system, with a neural network as a proxy function for Zemax or Code 5 itself. And so what are the optical design parameters? It can be individual radii, surface descriptions, description parameters, can be different spacing parameters, different material types. All kinds of different parameters can affect these optical PSFs, which describe the characteristics of the overall optical system. So now what we can do is, in a similar approach like before, we can consider parameters, these parameters that I just mentioned, and we can generate a data set using Zemax forward ray tracer black box function, as far as we're concerned, produce outputs that we can use for training. And here's our PSF generator network, which generates a PSF at a certain field and a vignette factor. And what we have here as an architecture is, and we can define the loss function to optimize that network, but what we have here as an architecture is a network that consists of an MLP and a convolutional decoder to produce those output PSFs. And as before, we can learn the weights of this network, the proxy Zemax, if you want so, by sampling through different parameter settings, and then using this as a training data set, optimizing a loss between the PSF, the vignette factor, and the ground truth simulate forward model with the complex Zemax ray tracer, and finally fix this model. Then again, what we can do is similar like the ISP optimization before, is we can optimize for optimal PSFs. In this case, we can optimize for tiny spot size here. And you can see here the result of the optimization of the parameters, so gradients backpropagated all the way through the to the individual input parameters of the optical system. And we can do well and design an optical system in this end-to-end fashion. So we have validated this approach and built actually several optical systems for natural imaging, for display purposes, object detection, traffic light detection. And each time we get a different optical design tailored to the domain-specific use case. So what we have here in this first case is an optical design that is optimized for natural image capture. And what we can see here, if you look at the sort of middle fields, that we get a design which has a much narrower tail, so we don't have such a long tail than the nominal design. And the nominal design, by the way, is a design which in this case here was designed for over 2 months by optics engineers that are trained to do this, find the best design, and tweak all the Zemax parameters, optimizer parameters in the best fashion. And this is what they came up with. We find a very different design. In this case here, what you can see here is that it has a larger F number. So we get a little bit less light efficiency through this one here, slightly peakier PSFs, and we can handle that on the reconstruction side fairly efficiently. In the ISP, it gives you slightly more noise in low light conditions. We can still recover that, but the overall sharpness here is drastically improved if we jointly optimize this together with our hardware ISP. We get a better output, which is visibly better here in this case. We get again yet another different ISP if you were to optimize this with a neural network, for example. Now let's have a look at automotive object detection. Entirely different PSF here. What we get is a very uniform behavior of the PSF, especially in the blue channel, and larger PSFs than a nominal design. And you can see that this actually improves detection quite substantially, although we get slightly more blur. In this case here, the F number is actually lower. So we do want to make sure that we get more light here in this design for object detection. And we can, on average, do substantially better. Here is the last example where we have a traffic light detection, so small objects at the periphery of the image. You can see here that for 6 degrees and 8 degrees, the overall extent of the sort of core tail of the PSF, which contains most of the energy, is contained to a smaller set of pixels, so you get less blur for those regions, and that helps to detect those small traffic lights. Here's a qualitative example, and you can see here that we detect substantially better. In all cases, we've done a quantitative evaluation, detecting up to from 5 to 10% improvement in mean average precision for these scenarios. So now I want to look at sensors. We've looked at the whole chain from ISPs to optics, but I haven't talked about the sensors. How can we use sensors and a smart design of novel sensors, robust new sensors, to overcome some of the challenges that we have in the edge cases that we talked about at the beginning of the talk? So let us have a look at a scenario like this one here in harsh weather, where we have a lot of backscatter affecting severely the LiDAR measurements. Here the first response is reported, and at the same time we have a lot of scattering that we see in our RGB capture, in this case here stereo capture. We can gate out some of these backscattered components affecting both stereo and LiDAR sensors by devising a new sensor that gates out some of these contributions. Gating works as follows: we send out a pulse of light, and we only record light that comes back to the sensor at the given time. Here you see 3 gated slices at 3 different temporal offsets, 3 different temporal gates that we capture in the scene. And you can see here that in the first slice, we have gated out all the far components, path with very long path lengths. In the second slice, we've gated out early components and long components. In the last slice, we've gated out everything that's early. So that allows us to gate out certain path of the light transport in the scene. We can take the sensor, bolt it on a vehicle, and it becomes nothing else than a simple gated camera source, diffuse flash laser source that can mount here below the bumper, and we add a camera behind the windshield. We can devise a 3D object detection architecture that uses these gated images in a very nice fashion. You can get 2D proposals out of these gated images because they're very high spatial resolution, other than existing LiDAR measurements. They are basically at the same resolution of RGB camera sensors. And at the same time, through the variations of the intensity in the gated images that we capture, we have depth encoded. So they also have a direct encoding of depth at this high resolution. That can be used and get really nice 3D object detection results. And it works well in harsh conditions. Here you see an example of a night capture, which is challenging for conventional RGB pipelines and stereo pipelines. And the proposed architecture works quite well here using these gated images. I can show you an outdoor image here. There you see color-coded the 3 individual gated slices in red, green, and blue. And here's some more harsh cases in dense fog. And again, completely different image modality. Here we use a very tiny data set, 10,000 samples to train this network. But for fog, even at long distances, this approach gives robust object detection results. another scene for fog. You see some pedestrians that are actually there on the side of the road. Here, an overland drive, also very challenging. Not much you get in the RGB captures in this case, which are not shown here, by the way. But you can get nice results with very long distances, which is in very, very sharp contrast to LiDAR measurements, which do not work in these cases due to backscatter, and they have a low resolution at long distances because of the angular scanning approach that these LiDAR scanners are using. Now, another thing that you can do with this new sensor modality, images, is train other models. For example, a model which we call zero scatter, which takes as input RGB images, so affected by the haze and the scatter in the scene, and produce images that have this scatter removed. So how can we dehaze, defog, desnow these particular scenes, these RGB scenes, using a neural network? We can do that by using gated images as a loss function. We can, on the resulting images that a dehazing network produces, define a loss that simulates gated images, and then measures the difference to the actual gated image, uses this as a loss function to train the network weights of this dehazing network, which works because these gated images are not affected as much as other modalities by the backscatter in the harsh scenarios. Here's an example what this accounts to, and you can see here that especially for long distances, we can get really good dehazing results with this approach here under challenging conditions. These are all unseen scenarios, of course. Here's an example in fog that shows you that you can do quite a bit with this approach as an indirect way to supervise our existing image-to-image models. So far I've talked about different approaches that tackle the whole camera and vision chain, all the way from photons in to the optics, through a particular sensor, different sensors, through the ISP, through a detection network, to an output of that particular detection network. But what I haven't looked at so far, and what I alluded to at the beginning of my talk, is the scene itself. So how can we reduce ambiguity of the scene by making the scene differentiable itself? And this is what we're going to do here in the last portion of my talk, which introduces the concepts of so-called neural scene graphs that we can use for inference and data generation. Let us look at a dynamic automotive scene, such as this scene here. It's just a scene from the Kitty dataset. If you take a frame T at a given time, then what we propose is to model this entire scene with an implicit scene representation that is based on scene graphs. So what is a scene graph? We consider all the dynamic objects in the scene, all of the vehicles here in this case, then they're all the nodes of this particular scene graph. A scene graph is nothing else than a directed acyclic graph. And at the edges of that particular scene graph, we have transformations that transform the objects to their particular positions in the 3D scene. Such scene graphs, seemingly very simple, are a very well-known concept in computer graphics, have been explored there for a while to model complex compound scenes that consist of many different objects. So how do we represent this entire scene? This image here, just an array of pixels with a scene graph, an implicit neural scene graph. So we first take out one specific object here. Let's, for example, take the truck here of interest, and that now is a node of the particular scene graph. We assume that we have, let's just assume we have its bounding box comes from a tracker, for example. And what we can then what we can then do once we have a transformation of the bounding box in the 3D scene is that we can shoot a ray from our camera through this bounding box. And at every location that we sample the bounding box, different sampling schemes that we explore, we can sample the radiance, which we represent with an implicit neural radiance field, representing this particular truck object. We can collect the radiance, can integrate it, and then we get only the radiance that is reflected from this particular point on the truck. And we do that by introducing one model for all the trucks and all the vehicles. That is one implicit model for all of the objects which are from the same class, for example. So now, what do we use in order to represent the radiance? We use a neural radiance field, a NERF, super popular neural rendering approach. And what we do here is, instead of using a typical NERF here, we implement it as a two-stage model where we give not only the location, the direction that we want to sample the radiance in, but also the location of the particular object, P here in the global scene, and a latent code. Latent code encodes differences between the individual object instances that we represent with our model, and the position that we input here, P here in this case, makes sure that we encode global illumination effects depending on the position of the vehicle or the object that we want to represent in the scene, depending on the position where it is in the scene, depending on the illumination. So we add these two inputs to a conventional NERF that outputs color and opacity at every given location that we sample it at, and then we integrate those along array. So now we can do that for all objects in the scene, define them all as individual nodes with shared models. We use a few separate models for trucks and cars. Then encode these individual models with their latent codes that we optimize for during the training time, and then generate pixels by accumulating the radiance for all of these individual dynamic objects that we have in the scene. So all of the dynamic objects are now handled by individual modified radiance fields that we model in our scene graph. Now, what I haven't talked about so far is the background itself, the static background that does not change. For that, we just use a plain NERF, but we sample it in a slightly different way. So that it scales. We just use a set of planes, multiple planes that we sample this particular NERF at to get background components, static components in the scene that do not move. Then finally, we have a full array representation of the radiance through the scene. We take all of the samples of the dynamic objects and the static background objects and integrate them, which gives us a final image here. So this is the final NERF, gives us the full image that we now represent. So now if you want to represent a different frame of the same scene here, all what we have is we move these individual node representations around, keep the background as is if we don't move through the scene, and evaluate there again at a different location. So all of a sudden we have an implicit neural scene representation that allows us to modify scenes and change scene arrangements, scene configurations, generate entirely new scenes. And I want to show that here. So for example, we train our neural scene graph representation on a few videos from the Kitty data set. Then we can add trucks, move them around, put them at different locations, rotate them slightly. And all of this is consistent with global illumination cues, allows for occlusion and realistic rendering. Here's an example of global illumination effect. You see the highlights move along with the vehicle being moved. This is encoded in our particular scene graph representation. So Obviously, like regular nerves, we can also move into the scene and change object locations in the scene, change our ego location, and simulate entirely different scenarios of these captured learned scene representations. Finally, once we have such a representation, we can use this for inference. We can take a scene graph and optimize it so that it matches an input image. So how do we do that? Let's say we have this as an input image, here the ground truth bounding boxes are overlaid from the Kitty data set. Let's assume we have a neural scene representation, neural scene graph as described. Then what we can do here is, so here we start with a sample of this particular neural scene graph, somehow initialized, there's different approaches that we have explored. And then we optimize this scene graph to produce as an image that is as close as possible to the input image, just by optimizing the latent codes and the transformations of the individual nodes. And that gives us a representative image of that scene and an entirely different approach how to do object detection. We can obviously also use neural scene graphs to generate very large training data sets of pseudo-simulated data and train feed-forward networks to do object detection or other perception tasks on these relatively large data sets. So in summary, I've shown you a number of approaches that tackle edge cases, the harsh cases that we have to handle in perception systems by designing systems in an end-to-end fashion, particularly looking at the entire camera chain, including post-processing, sensors, optics, and the scene itself. And I'm convinced that such perceptual cameras will allow us in the future to overcome a lot of the challenges that we have with today's supervised training approaches, especially when we're at the point where we can generate large data sets of pseudo-simulated data with neural rendering approaches. We're at the stage where we can use these to train our existing models and can generate conditions which are otherwise difficult to see. So more decomposable, interpretable networks handling the edge cases exactly where they're happening allows us to achieve some of these scenarios, which are in fact superhuman vision capabilities, such as seeing in fog and snow and other challenging conditions that for us as humans are sometimes unsolvable. So with that, I'd like to thank you all for the interest in my talk, and I'd like to highlight that some of the results and papers that I've mentioned are all on my webpage, which is shown on the title slide and this last slide here in the slide deck. So with that, thank you all.
Yeah, with that, I would like to thank the speaker for the very interesting and inspiring talk. We would now have time for a Q&A session for Felix Heide. He's here. So feel free to ask your questions, whether on YouTube or in the Zoom channel. You can also raise your hand if you want to ask some questions. In the meanwhile, I would like to start with one question. So thanks again for the very interesting talk. My question would be, you're heavily advocating image processing algorithms for vision sensors to model them from hardware to software side. So do you believe that advances in algorithms will make active sensors such as LiDAR unnecessary at some point?
I wouldn't say completely unnecessary, but they can definitely play a major role in having a stack that is highly redundant. So having a stack that has a fully redundant LiDAR processing stack and a fully redundant portion that relies only on vision, I think is a really important piece for autonomous vehicles. Some of the ideas that I think will make a big difference, and particularly moving the processing pipeline, early vision processing pipeline from hardware to software, can also be applied to LiDAR processing. If you think about the thresholding algorithms that are used in single photon based LiDAR, all of those can also be optimized in a similar fashion. I think in general, just moving away from a fixed function hardware to learnable software is the right thing and has to be done on the low-level processing side. That's my view on it.
Yeah, thanks a lot for elaborating this. I think that's quite an interesting field, and this is also like something where I would have the next question. It goes in a similar line because I mean, naturally, sensor fusion is known to be a very challenging problem. So, with your differentiable way of thinking of the design, do you think it's kind of possible to design, let's say, a compound sensor made of multiple sensors, such as cameras, LiDAR, and radar, to compensate each other, like even already on the hardware level?
Yeah, exactly. So really good question. This is in fact a very active direction of research that my group and a few other groups are looking into, and this is exactly what we think may happen. So we're just at the start of designing some of the sensing blocks and processing blocks together. Most of this has been done on the camera side, but once you go to multimodal systems, I think there's a huge potential for exactly these algorithms working together very collaboratively, even based on the conditions as well that you're sensing in, so they could adapt dynamically on the scene content. We have and last CVPR had a paper on auto exposure, for example, that does something similar like that. So there seems to be a strong indication that this collaborative behavior could be something that these learned systems will be able to do very early on in the pipeline.
Yeah, thanks a lot. That's quite interesting. We have another question from YouTube. So the PSF modeling is it done for global shutter or rolling shutter imaging system, or is it kind of independent?
Yeah, so really great question. The PSF modeling can be applied both to global shutter as well as rolling shutter systems. So that system is something that is really flexible. All of this is happening on the optical side, right, before any sensing or readout.
Okay, thanks for answering. I feel like the neural scene graph representation you showed, the results are very impressive. However, to train such networks, it needs quite some additional input sources, for example, from a detector and tracker, etc. So what do you think, like how far are we away from, let's say, watching the video only without other inputs to train such a network?
Yeah, so but again, super active area of research, and I think this is really the right question to ask. How can we get to scene representations that are fully supervised just by the scenes themselves, by just observing videos? And I think we're sort of slowly getting there. If you look at some of the very recent work in neural rendering, which is frankly exploding in that area. There's a bunch of models now that allow decomposition of scenes and are starting to learn decompositions. Reasoning over classes is still somewhat tricky. The big downside of all of the early neural rendering works is that they are overfitted to a single scene, right? So now the research community is making the most logical next step in trying to find models that are naturally decomposed. And I think over time we'll get less and less reliant on some of the explicit input, but in order to really make that happen, we first need to get these models to be efficient. Right, they're just way too slow in order to do really complicated meta learning tasks. So there's a lot of work in that area where you're just trying to remove this volumetric sampling that is very essential to all of the volumetric methods with some light field based approaches. So super active area, but I think the first step is making them efficient, and then disentangling larger distributions of scene objects, making decomposable objects, decomposable models, next logical step.
Yes, thank you. So you've been talking about also like making them more efficient. Like, what are your personal clues on them to make them efficient? Like, what do you think needs to happen over the next 2-3 years to really make them efficient?
Yeah, so we definitely have to go to a sort of local light field based model, right? Where maybe you can get away with some proxy geometry, some geometric scaffold that has also been heavily explored, and that could be good enough so that a light field lives on it, that I only have to evaluate once, right? That would be the key thing. And then I think this has to be joined together with some of the recent advances in scene understanding, right? So we have to be able to disentangle dynamic objects, what the functions of the individual pieces are, in order to make the next logical step and learn over large distributions. But I think all the basic building blocks are starting to form. So folks are trying to make these models really efficient, and a lot of ideas from computer graphics can be applied in this sort of new field, subfield of 3D vision. So I'm super excited about that. So we're sort of reusing some of the early ideas in computer graphics right now around efficient data structures, and there's a lot of research that could be applied, a very rich field that can be applied in order to make some of the learned models more efficient.
Yeah, thanks so much. It's a very fascinating field and fascinating research, and thanks again for your very inspiring and interesting talk. It's super interesting for the audience, and I think we have to move on to our next speaker. So thank you, Felix, Heide, again for being here and giving this great talk. We would continue with our session. So it is my great pleasure to introduce our next speaker of the workshop, who will be Torsten Sattler. Torsten Sattler is a senior researcher at the Czech Institute of Informatics, Robotics and Cybernetics at the Czech Technical University, where he's currently building up his own research group working on 3D computer vision and machine learning as part of a tenure-track position. Before, he was a tenured associate professor at Chalmers University of Technology and a senior researcher in the computer vision and geometry group at ETH Zurich. Torsten obtained his PhD from RWTH Aachen University in Germany. His research interests include large-scale image-based localization, real-time localization, and SLAM on mobile devices, 3D mapping and reconstruction, augmented and virtual reality, machine learning, and self-driving cars and other autonomous robots. His current work focuses on making algorithms for localization and mapping smarter by incorporating higher-level scene understanding. Torsten's research is very well known, and he published papers in all major computer vision and robotics conferences. Furthermore, he is very active in the community by serving as associate editor, area chair, and program chair for many conferences. He is also co-organizing workshops and tutorials on visual localizations. So it's our great pleasure to have you here today. And without further ado, Torsten, the floor is yours. Torsten, I think you are muted.
Okay, that should be better. Thank you very much for the nice introduction, and thank you very, very much for the invitation. I've been following the workshop, and it's a really nice workshop. I'm going to talk about recent developments in visual localization, and particularly I'm going to talk about this paper that Simon mentioned before. But before we start, I would like to thank all the amazingly talented people that I was lucky enough to work with. These are some of them. These are those whose work I think is mentioned or influenced what is shown in this talk. And without them, the works that I present would not have happened. So I'm going to talk about visual localization, as is the title of the workshop. And just for clarification, I'm talking about the version where we want to compute the exact 6 degree of freedom position and orientation from which an image was taken with respect to some scene representation. Besides self-driving cars on autonomous driving, this includes applications in augmented reality. So on the right, you see this AR navigation in Google Maps that Simon, I think, mentioned, and that is driven by Simon's VPS. Another interesting application, and this is joint work with Vladimir Guzov, Ayman Mir, and Gerard Ponsmall, is performance capture of humans. So here you see we had a head-mounted camera as well as IMU sensors on the body of multiple humans, and we used the camera to essentially figure out where they are in the scene. and the IMU sensors to estimate the body pose, and the body pose and camera pose are jointly estimated because they give you constraints on each other, and this can be used to track the motion of humans in large-scale scenes without actually having external cameras. Okay, and what makes localization challenging, and this is also what you saw in the challenge of this workshop, and this is also a topic of a workshop that we are going to organize on Sunday, is that the world is not static, but appearance and geometry can change quite a bit. As you see here in these three pictures, these depict the same place in front of my office at ETH when I was there. And this is taken at different seasons under different illumination conditions. And even for humans, these are quite drastic changes. Still, localization algorithms should be robust to this kind of changes if we want to have self-driving cars that operate reliably at any point in the day, at any point in the year, or have persistent augmented reality applications. What I want to start with technically is a small taxonomy of localization algorithms. This is not the only way that you can divide them, but this is the way that I'm going to divide them here. I'm going to divide them into two parts. One is image-based representations, where essentially our scene representation is a set of images with known poses, and these are used to estimate the pose of a query or test image. The simplest version of this is image retrieval. So given a test image, I figure out what's the most similar database image and approximate the pose of the test image by the pose of the most similar database image. You can do slightly better than just taking the top retrieved pose by essentially doing some sort of interpolation between the poses of the top retrieved images based on their visual similarity to the test image. You can, if you want to get something of similar accuracy, can train a network such as PoseNet that takes in an image and outputs or regresses the pose. And these are mostly approximate. So they are, in terms of accuracy, they are still far away from what you can get with state-of-the-art localization systems. But you can actually get accurate poses using image-based representations. One approach is if you have the query image, you compute the relative pose to the top retrieved images. The relative pose only gives you an idea of where the query image is with respect to this retrieved images. But since you have multiple images, you can essentially triangulate the position of the query image. And this can work very accurately. Rather than computing the relative pose from feature images, you could also train a network that takes two images as input and regresses the relative pose between them, either in the form of epipolar geometry or including the scale of the translation. And you could then integrate this into a pose triangulation. Another approach is so-called semi-generalized relative pose. So in this case, you match features between the query image and multiple database images of known poses. And these, then you can compute the relative pose between this multi-camera rig that you essentially construct and the pinhole camera. And you can do this both in general scenes or in planar scenes where you have a semi-generalized homography. Again, this can also give you accurate poses. The second set of methods are structure-based methods. So they use 3D structure in some form for the scene representation. So classical one is feature-based localization, where you have a 3D point cloud. Each 3D point is associated with one or more image descriptors. You have a query image, you extract descriptors, you match them against the descriptors associated with 3D points. That gives you a set of 2D, 3D matches that you can use for pose estimation. A more recent version of this is to not explicitly extract features and match them, but rather train a CNN that predicts for each pixel in the image what the corresponding 3D point coordinate is in world coordinate systems. And again, that gives you 2D, 3D matches that you can use for pose estimation. Another approach is that assuming that you actually have an initial estimate of the query pose, you can avoid explicit feature detection matching, rather just do pose refine. So the idea is that you project the 3D points that are visible from the initial pose into your image. You compare features associated with those points and descriptors extracted densely in the image. And from this, you essentially compute an update to your pose so that you get a better alignment of the projections. And you can do this a couple of times iteratively until you get a final pose. This taxonomy is, this is not an absolute division into two sets of methods. You can also have hybrid things. So for example, hierarchical localization approaches first use image retrieval to figure out which images, database images are similar to your query, and then they restrict feature matching to only the points that are visible in the retrieved images, which makes the whole thing more scalable and also more robust against condition changes. Or you could have a hybrid pose estimation stage where you partially have 2D 3D matches and partially have 2D 2D matches, and then use these for pose estimation. And what I will focus on in this talk is essentially the relation between feature-based methods and scene coordinate regressors. And I'm going to talk about pose refinement. We are going to present a paper tomorrow, I think, on this semi-generalized relative pose / homography. And we're also going to have a tutorial on localization that covers essentially all of these techniques. Okay, well, let's start with talking about comparing feature-based methods with scene coordinate regressors. How do we do this? Well, this is computer vision. We're going to run these methods on benchmarks and compare the results. And this is what people have reported in the literature. This is results on 2 indoors data sets measured as a percentage of images localized with 5 degrees and 5 centimeters. So higher is better. Color coding wise, you see feature-based methods in green, both those that only use RGB and those that use RGBD images in one form or another. Scene coordinate regressors are in purple, and again we mark whether they use only RGB or also RGBD. And these results have given rise to a couple of common beliefs that we find in the literature. So one thing is scene coordinate regressors are actually more accurate than feature-based methods in indoor scenarios, as here the top performing method or methods in this case are all scene coordinate regressors. And similarly, if you use RGBD, you get better results indoors than if you only use color images. As you can see here, you get better results using depths than without it, or at least similar results. On outdoors, you have different, slightly different pictures. These are the Cambridge landmarks datasets from Alex Kendall's PostNet paper and the day images of the Aachen day-night datasets. Here, this is median position error, so smaller is better, and this is percentage of images localized within 25 centimeters 2 degrees, so higher is better. And here you see that feature-based methods are clearly better than scene coordinate regressors in these outdoor scenarios or also at larger scenes. So this is what has been reported in the literature, but let's try to have a bit of a closer look at this. So let's first have a look at what you actually measure in a benchmark. So let's assume you have a pose estimated by some algorithm A. And what you want to do is you want to compare it against the ground truth. So you want to measure the difference in position and the difference in orientation between the ground truth pose and the pose estimated by the algorithm. The question is, though, how do you get the ground truth poses? What you need is essentially like a 6 vector that gives you a 3 degree of freedom position and a 3 degree of freedom orientation. And how do you get this accurately? Well, as in other data parts of vision, you could ask humans to annotate this. But I don't think humans are really good at all at predicting like 6 off-camera poses. At least if you would show me an image in a scene, I could not predict like 6 accurate coordinates. I could annotate matches, so I could annotate which pixels in one image correspond to which pixels in another image, but even that gets tedious and doesn't really scale that well. So this is typically not done in the literature. We could use some sort of external sensors, so a differentiable GPS, a Vicon system if we're indoors, additional sensors if they're available. But that's also not always that easy. So imagine you want to capture many different indoor scenes and also at scale, then mounting a Vicon system at each such scene actually becomes a hard thing to do. So there is also limited literature on using these like external sensors. What people typically do is they use some algorithm, structure for motion, SLAM, others, that generate a pseudo ground truth. Pseudo in the sense of that they're not actually measuring the ground truth, but the assumption is that the output of those algorithms is close enough to the ground truth that the distinction doesn't matter. So what localization benchmarks actually measure is how well an algorithm is able to replicate the output of the algorithm that generated the pseudo ground truth, which should naturally lead to the question is, how important is it how I generate my pseudo ground truths? Does this have an impact? And the ideal answer should be no. Whatever algorithm I choose to generate my pseudo ground truths, assuming that it's a reasonably good algorithm, I should always get the same results when evaluating methods on this. So let's look at this and see how well this actually holds. If you choose a pseudo ground truth, the first thing that you have to answer is, what do you actually want to optimize in the algorithm? So for example, if you have depth data available, you could optimize an error in 3D that minimizes a point-to-plane distance. And this is typically done in depth-based SLAM systems. If you don't have depths, you're most likely going to optimize some 2D reprojection error, such as typically done in structure for motion, or you could do a weighted combination of the two. So let's compare two pseudo ground truth versions qualitatively. This is the pumpkin scene from the 7 scenes dataset. And in orange, you see the ground truth trajectory released with this dataset that was computed using some depth-based SLAM technique, more precisely Kinect fusion. And in blue, you see the different version of pseudo ground truths that we computed using Coleman. As you can see that in some parts, those two trajectories line up quite well. In other parts, not so much. And this can actually quite impact your results. So this is the pseudo ground truth that you get when you use Kinect fusion. And that's the red trajectory. Green points are poses estimated by active search, which is a rather old technique. This is what I did in my PhD, was published about 10 years ago and uses classical SIF features. And if you visualize this, so you reproject the dense 3D model that we have into the image using the estimated poses, then there's actually a lot of jumps in inaccuracies. And the typical explanation was that, well, you're using sparse SIF features. This is not very well textured scene. This is probably the best that you can do. If you want to be more accurate, use better features, or even better, use dense features. Interestingly, if you switch to the pseudo ground truth that you get from SFM, you see that active search, this nearly 10-year-old techniques, is actually able to, for most images, predict a quite accurate pose. And it's very close to the ground truth. There's still a bit of jumps, but nothing that you could probably do, filter out with some temporal smoothing. So just switching the ground truths, you make a method that does not work that well, perform actually quite well of this data set. Let's look at a second method, DSEC star, which is a scene coordinate regressor. In this case, it uses RGBD data, where, so what it does is it first predicts for each pixel in the image the corresponding 3D point in the world, and then uses the depth values for pose estimation, by essentially aligning locally observed depths against the 3D points in scene coordinates. And this was published this year in PAMI. On the left, you see the results of DSEC star on the Kinect Fusion ground truths, and it's able to replicate this quite accurately. On the right, you see the results compared to the structure for motion ground truths, where it's mostly doing fine, but there are areas where it's actually quite off and consistently off. If you compare this against active search, then you see that on this Kinect Fusion, the original ground truths or pseudo ground truths, DSEC star learning-based method is clearly better than the 10-year-old SIFT-based approach, as you would expect. If you are looking at the structure for motion through the ground truths, you see that this 10-year-old method is actually more accurate than this learning-based approach. And this is not the result that you would like to see when it comes to benchmarking methods, because it actually raises important issues of how much can we trust the results that we see. I see that there's a question. If you have, we can also answer them now. Okay, was not a question. Never mind. But of course, this assumes that both pseudo ground truths are equally valid, right? So let's look at this. Let's try to answer whether there's one pseudo ground truth that's clearly better than the other, or whether we should consider both as valid. And figuring out when a pseudo ground truth is better than the other is actually not that easy. So if you visualize structure motion point clouds, then you see that you get much clearer point clouds with structure motion than if you take the Kinect Fusion poses and just triangulate the scene. That's probably not that surprising. Structure motion optimizes for like good point clouds. Kinect Fusion does not. So it generates a lot of clutter because the reprojections are not that accurate of local features. If you look at like a dense visualization, so we take the poses that we get with structure motion and Kinect Fusion and the depth maps that we have and just fuse them into one model, then we get the following. So on the left is Kinect Fusion, on the right is call map. And you see that Kinect Fusion actually gives you a slightly bent reconstruction, where this call map is globally more consistent, and also in the background, call map gives you clearer results because this is where most of the feature matches are found. But for foreground objects, you actually get clearer results for Kinect Fusion than for call map, likely because there are not that many features found on these objects. So this part of the scene is actually not like that well represented in the poses. And you can see similar results on other data sets. So this is apartment 2 living from the 12 scenes data set. On the left, the depth space slam is not Kinect Fusion, it's an error, it's bundle fusion. And on the right, you see what you get with call map, and you see with call map, you get globally more consistent layouts. But if you look at details, then the depth space slam approach gives you much crisper detailed structures and call map. And our conclusion was that there's not really, out of the two ground truths that we look at, there's not one that's clearly better than the other, but rather both seem valid to us. They both have their advantages and disadvantages, but they both seem like reasonably good approximations of the scene. So if we consider both ground truths, then we get the following. So let's start with the Kinect fusion ground truth, which was essentially used to build come to a set of common conclusions that we accept in the literature, such as classic methods do not work well because active search is actually clearly worse than newer methods. Scene coordinates regressors outperform feature-based methods. DSEC star is clearly better than feature-based methods. And if you have depths, you get better results than without depths. RGBD DSEC star is better than RGB DSEC star. Similarly for this feature-based method that uses dense flood for retrieval and R2D2 features for feature matching. However, if you look at the ranking that you get with the structure motion ground truths, then this changes actually quite a bit. What you see now is that active search actually outperforms all other techniques. So the conclusion that classic methods do not work well indoors is nothing that you can draw from this pseudo ground truth. Similarly, you see that active search is nearly 10-year method outperforms scene coordinate regressors. And we also see that the RGB versions of our methods are better than the RGBD versions for this pseudo ground truth. So in other words, conclusions that we accept as given from the literature strongly depend on the pseudo ground truth that was used to benchmark these algorithms. So switching pseudo ground truths from one valid pseudo ground truth to another can significantly impact the orderings. Which naturally leads to the question, how can we actually still compare algorithms? One way is to, if you have two ground truths, is to look at Pareto optimality. So here you see the results on the structure motion ground truths and the depth-based SLAM ground truths, pseudo ground truths. And you can compute the Pareto form, which is essentially everything that's above and to the right would give you a new state-of-the-art method because it's better on one pseudo ground truth than an existing data point, while not being worse on the other. So here, if you could compare methods by figuring out, do I beat existing methods on one axis, and am I not worse or slightly worse on the other axis? The other thing that we actually propose in the paper is to actually to take the similarity of methods to the pseudo ground truth algorithm into account. So you could color code your methods by essentially saying what is colored green here are methods that optimize a similar objective as the pseudo ground truth. RGBD DSEC star minimizes some alignment in 3D, similar to the depth-based SLAM pseudo ground truths. Red is methods that optimize a different objective, 3-projection error instead of a 3D error, and blue is something that is somewhere in between. Unfortunately, that might actually not work that well. So for here, for example, you see the same color coding as for the other ground truths. And if you just compare methods here in red and here in green, then you still see that you get a slightly different, you did get a different ranking in this block and in this block. So I was just saying, I only compare methods that are comparable and that don't optimize different cost functions might not work that well. So the lessons that we learned here is that the choice of pseudo ground truths actually has a much larger impact on localization rankings than we actually thought, which should lead to us critically questioning some of the results that some of the conclusions that we've drawn from existing results. I think there's a lot of interesting work to be done here, especially when it comes to going away from creating different pseudo ground truths and evaluating them, and towards understanding the relation between the different pseudo ground truths and whether we can predict what's the best accuracy for a certain set of methods is under a given pseudo ground truth. And another interesting question here is whether, if we want to have a fair comparison between methods, whether we should simply switch to synthetic data. And here's one thought to this. So here you see two real images taken with the same camera. And if I run a state-of-the-art feature matcher, I think this is Lofter, and oh, this is Superpoint and Superglue, then you get around 1,000 inlier matches, which is pretty good, but also not that unexpected, given that those images were taken from similar viewpoints under similar conditions. Let's do the same experiment in a synthetic world, where we used reality capture, which is the state-of-the-art 3D reconstruction software, to get a colored mesh. And as you can see, some things, artifacts aside, you actually get very good 3D reconstruction. This is probably state-of-the-art. But if you do feature matching here, you get about twice as many inlier matches with the same method. So my take on synthetic data is that there's something that, at least for the current generation, seems to make it too easy, too consistent, and local features seem to be latching onto this. So you get many more feature matches, or you might get more feature matches than you expect. So there seems to be something missing, probably some low-level noise that we're currently not modeling. But I think it's an interesting direction of looking at, and especially neural radiance fields, such as NERF in the wild, which can model different viewing conditions. I think this is a very interesting direction to look at, or fully synthetic scenes, such as those available on SimLogMatch. Okay, that concludes this part of the talk. I think we started 10 minutes earlier. So I will, I think, quickly go through this part and then wrap up the talk. So let's look at, do a brief recap of hierarchical localization methods. The idea was that we have some 3D structure, we have our query image, we retrieve a database image that's similar to the query, we figure out what are the 3D points visible in those images, and then restrict feature matching or 2D 3D matching to those 3D points. And this works well. This gives you state-of-the-art results, but it also raises some questions. Do we really need explicit feature detection matching, or could we just start with the pose of the retrieved image, which we're currently completely neglecting? And this is a paper that we presented last CVPR, which essentially does pose refine. The idea is you have a query image, you have the retrieved image, you know which 3D points are visible in that image, and you can assign features extracted from the retrieved image to those 3D points. Then you run a CNN on the query image, you get a set of like dense feature detections, and starting from your initial pose estimate, you project the points into the image, compare the features of the projection points against the features in the image, compute residuals, and then use those residuals to refine your pose estimate. And you can do this a couple of iterations at different feature resolutions until you converge. And here's an example of how this operates in practice. So this is the current estimate of the query pose. This is reprojection of, the red is the projection of the base of 3 points based on the current pose estimate, and green is the ground truth projection, which we're not using here, but it's just there for reference to show that it's actually converging to a pose that is accurate. This whole thing can be trained end-to-end with only a pose level supervision. So what we're doing is we're looking at pairs of images and known poses and known 3D points. We run a unit architecture and then do course-defined alignment we predict some set of confidences for each pixel, expressing whether we believe this pixel is likely to be useful for pose estimation. We compute features, and based on the current pose estimate, we get features for the 3 points from the reference image and project those into the query image. We get residuals, and then we run a Levenberg-Marquardt algorithm for a fixed number of iterations. And here we actually have a learnable damping factor, which could, for example, model that certain sets of movements, such as in-plane rotations, are unlikely in certain scenarios, such as self-driving cars. We unroll the optimization, run it for a couple of times. And the loss set we essentially minimizes the difference between the current estimate and the ground truth pose. And we do this for different levels of the unit, going from coarse to fine. And this, since it only predicts features and not geometry, generalized actually quite well. So this is refinement results on indoor scenes when only training on outdoor data. So this works quite well. What's interesting, I think, is that it's able to learn like feature confidences just using pose supervision. So here you see what it has learned for a self-driving car scenario, where red means the network thinks this are useful pixels, blue means pixels that are not useful and ignored. And you see it has learned to ignore cars, and instead it focuses on boundaries, because this is for alignment. This makes sense. Okay, so for this part, we had looked at directly refining camera poses based on feature consistencies instead of explicitly matching features and computing matches. This is essentially the same thing as like a robustified version of direct refinement, such as done as LSD SLAM. And we're not the first ones to do this. So von Sturmberg and others, essentially Daniel Kramer's group, has done work on this before. What is, I think, interesting is that you're still using classical techniques, in this case Levenberg-Marquardt for training, but you don't need like pixel level correspondences or something like this, but you can just do it with pose level supervision, and you can even learn pixel level information from this. It seems to generalize quite well, but of course you need to have a good starting pose. And we're actually going to have to release source code for this. Okay, in the interest of time, I will skip the last thing and just do a bit of self-advertisement, which is we're going to present a couple of things at ICCV. So there's the paper that I presented on the limits of pseudo ground truth and visual camera localization. That will be in session 5 tomorrow. There's also going to be this paper on semi-generalized homographies in the same session. In session 8, we're going to present a new benchmark for auto localization, especially with a focus on autonomous driving scenarios, where we use crowdsourced data crawled from Mapillary to create very challenging seeds. On the 17th in the morning, we're going to organize a tutorial on visual localization, covering many of these things that I discussed now in more detail. And in the afternoon, we're going to organize, I think, the fourth version of our long-term visual localization on the changing conditions workshop. With that, thank you very much for your attention. And if there are any questions, I'm happy to answer them.
Yes, thank you very much, Torsten, for the great talk. We have a question on YouTube. If you have to choose a single reference algorithm for getting pseudo ground truths to train the newly designed visual localization method, what would you recommend the reference algorithm to be? Colmap?
I mean, I'm a big fan of Colmap. I use Colmap by default. I think the main message is I don't know what would be the best choice for as reference algorithm. If you If you want to make your method look good, do what Simon suggested and essentially build a reference algorithm that is close to yours. So for example, if you're using a feature-based method with some learned features, run structure for motion with those features. And then this should ensure that the results that you get for your method actually have a very good chance to be the best. I think we should look at this in a slightly different, from the other way around, saying if I'm able to capture my scene using this type of algorithm. So for example, for the data set used in these challenges, it was some SLAM method that used IMU and I think some direct alignment. Maybe the type of localization algorithm that I want to use on this data set, something that mimics this algorithm that generated the scene representation. Because there the hope would be that this has the best chance to give you consistent alignment between new images and the old ones.
Okay, thanks a lot for the answer. Another question, what would be your approach to generate reliable ground truths, especially for indoor SLAM environments, considering that obtaining accurate 6 degree of freedom poses is generally quite challenging? I think it not only holds for indoor, but maybe also for outdoor.
Yeah. So essentially what you want to ensure is that, so talking in the localization scenario, that your ground truth is at least 1 order of magnitude or more accurate than what you can achieve with the localization system. So what you can do is try to use as many sensors as possible. So instead of a single camera, use a multi-camera system that gives you a larger field of view, which should stabilize the whole pose estimation process, helps when parts of the scene are not that well textured because you also see other parts, and should ensure that you get more accurate poses compared to what you can get from a single image. Use a Vicon system or like an external camera capture sensor if you can, but be aware that, again, you're changing from one algorithm generating pseudogrounds to another that will also have its inaccuracies and so on, but most likely be like this order of magnitude more accurate than compared to what the approaches that you evaluate on this data set can achieve.
Mm-hmm. Thanks a lot. We have another question from YouTube. Even with measurement devices like LiDAR, isn't yet another objective function minimized to produce pseudo ground truth poses, introducing yet another bias?
Yeah, I mean, yes, that's whether you use like a structured light sensor for RGB SLAM or LiDAR to get the depths. That's essentially you minimize a different cost function. Here, some 3D alignment compared to methods that would optimize 2D 3D alignment. Your local minima will be slightly different, and methods that optimize the same cost function will, I guess, have a higher chance to land in a local minimum close by to the pseudo-branches.
I think another very interesting following up question from Max here in the chat is like, have you or anyone looked into fusing these various ground truths or reference poses methods to account for the limitations of any singular one?
That's a good question, and I think the main question is how would you fuse this? I think there are multiple ways that you could try out. So one thing would be to compute relative poses with all methods, and then essentially do some global structure motion that jointly estimates all poses under those relative pose constraints, or do some sort of pose graph optimization starting from one pseudo ground truth that tries to move all the poses in a way that they're consistent with like the relative measurements that you get from both types of pseudo ground truth algorithm. But again, it's most likely in practice not that easy, in the sense of that if you have different noise characteristics that you will need to take into account when like doing a weighting between the different measurements. So I think it's a very good question. I think there's some interesting work to be done there, but I don't think that there is an easy win to be had here.
Yes, thanks. I think it's quite an interesting and challenging problem, to be honest.
Yeah.
Maybe to conclude, let me ask the last question from Marcel. I think it's going in a similar direction, but what he wants to know is, I am very curious to know which algorithm to obtain a ground truth would be closer to some ground truth taken from an optical tracker system, e.g. for a small controlled environment. Is there any insights on that? And is there any way to scale that? Could you comment on that? Thanks.
I don't think that I'm not convinced that there's a general answer to this. I think it's scene dependent. So if your camera is close to the scene, then I guess you will have an easier time with a depth-based approach, because you actually get accurate depths because they're close to the cameras. If your scene is further away, structural motion might be, like feature-based methods might be better, because the accuracy of the depths that you get from a sensor, or the inaccuracy of the depth of the sensor, grows quadratically with the distance to the camera. And for structural motion, you can just have larger baselines for triangulation. So I don't think that there's a general answer to this. There was a second part to the question, but I forgot. What was it?
I think what was mainly about like scaling.
So scaling is the issue, right? So if you have a small controlled environment, you can use a Vicon system or something. If you go to a more complex scene, you need to ensure visibility of the sensors that you put to your camera, or your camera system. I unfortunately don't have a solution there. What might help is if you get partial ground truth, so you have sensors in parts, so that you can get like accurate poses in these parts, and then weakly connect them using SLAM or something like this. It also touches on a different question, whether you really need to have a globally accurate map. For some applications, you probably won't. For some applications, you won't. Probably don't need. So if you think of like augmented reality applications that happen in rooms, then you want to model those rooms accurately. The transition between the rooms probably doesn't need to be that accurate. As Alex Kendall made the point today, you might not need like super accurate high definition maps for self-driving cars either. So it might be that in the end, all you need is local consistency, at least for some applications. And then you are at an easier problem.
Yes, thanks a lot. I think this is a nice closing statement. So thanks a lot for your great talk, Torsten, and also for the great answers. And so we would move on to our last speaker of today. So our last speaker will be Professor Wolfram Burgard, and he is a professor for computer science at the University of Freiburg, where he heads the research lab for autonomous intelligent systems. Furthermore, Wolfram Burgard is vice president for automotive driving technology at the Toyota Research Institute. Wolfram's research addresses the development of advanced techniques for robot perception, navigation, manipulation, and learning. In particular, he is known for his probabilistic approaches to the problem of simultaneous localization and mapping. Among others, Wolfram is fellow of the AAAI and IEEE. He furthermore is a member of the German Academy of Sciences and the Heidelberg Academy of Sciences. It is our great pleasure to have you here today, and without further ado, the floor is yours.
Thank you, Patrick. Thank you for the kind introduction, and thank you, Torsten, for the great talk. So I was about changing my slides, but then I decided to just leave it. And maybe I can also add some references to the problems that you discussed, and also discuss how this is potentially different in robotics, and maybe that could also stimulate an interesting discussion here. So what I'm going to talk about today is this question, like, and this is mainly I think the difference to computer vision, namely this question how we can build physical systems that can act in their world. And for that, if you assume that there's this model of the sense-act cycle, then that what you would like, or what you would have is something like a device that perceives the world, builds an internal model, and then generates actions that allows it to achieve their goals. If you think this in terms of navigation, right, then usually what you see is, and we saw this in the talk before as well, that you somehow start building a map from your sensor data and then use this map as a model to localize the robot relative to this map. And so this is how this basically like is done in most cases. While this is a robust approach, right, that this two-step process, it also comes with problems, and I'm going to talk about the problems throughout this presentation as well. So the key challenges when you really think about building physical systems is, first, like for industrial applications, you basically want to have accurate localization, right? And same is true with, depending on how you do this, with self-driving cars. If you like, there's several approaches where companies basically build high definition maps and then want to have accurate localization of the vehicle relative to these high definition maps, which basically then allows the vehicle to stay on the road and not leave the road, right? You also want to be able to robustly map an environment, like with less or with very, very little manual intervention, if at all. And then you want to have this thing that we call long-term autonomy, where you basically want to have the robot not failing for a long, long time. Right? That could be like, and this is challenging, particularly for mapping. If you think about dynamic environments that Torsten also spoke about in his presentation. And you find, in fact, in robotics, different types of representations. This can be grid-based representation, occupancy grids, point clouds, landmark-based representation, meshes, even textured meshes that are used for localization purposes. On the other hand, like, people tend to use not like, let's say, like incremental one perception localization or one-shot localization. In robotics, we typically rely on filters to assume stability over time or to integrate information over time, which would then be EKFs, particle filters, discrete filters, or optimization approaches, even like smoothing techniques. And here is like a visualization of particle filter localization works. It's known also as condensation in computer vision, although in robotics, you basically also add that what is called a motion model, because you know what the robot is commanded to, so that you basically have control over the movements of the camera. And that is the difference here, basically the incorporation of these movements and not assuming something like a constant velocity model. Also, and then you can do things like global localization, so you can put a robot into an environment and let it figure out where it is relative to this environment. So this is basically the standard technology, or one of the most popular approaches in robotics for localization. The key question is always, like when you talk to industry, how accurate can that get? And that also brings us back to that benchmarking discussion that we just saw before. And here's an experiment that we did with together with KUKA, and with the exact same question: how accurate can you actually get? And here you basically have the advantage that you can control the camera, and this is set up where the robot is supposed to navigate like repeatedly to the very, very same spot. Think about this as a situation where you do have a workbench that the robot actually has to approach and then do open loop manipulation, for example. The black stripe on the floor is just to visualize like the accuracy of this. It is actually measured with a motion capture system in this case, similar to a Viken system. And the advantage in this context is that the Viken system is very, very accurate when it comes to repetition. So basically, although the entire space might be distorted, because it in the end calibrates using least squares optimization approach, the overall, the repeatability is actually ensured because we just measure the difference from reference positions. And that's what we do here. We basically ask the robot to go back to a specific location and accurately localize there. And this experiment, the accuracy of that localization approach was so high that we observed, or that we had to distinguish between actually the positioning accuracy, basically how accurately the robot got back to the position, and the localization accuracy, basically that what the system believed where it was relative to the reference post. Because in some cases, the controller basically did not execute these incremental commands, and we basically told the robot, like, move 0.5 millimeter to your left, then the controller basically didn't do this anymore. So that's why we distinguish between the two. And here's another experiment where they did this based on LiDAR in this context. Where this 11-ton system, where we also introduced basically these wooden pieces, or they were basically meant to obstruct the field of, or the measurements of the LiDAR, so that it couldn't rely on as much map information as it had. We did the very same with the Vicon system. You see these tripods there in the background that actually measure the repetitions of, or getting back to the, or this homing, so to say. And here in this case, the accuracy with the beyond, like in the area of millimeters. And in fact, it got a little bit worse when it comes to dynamic environments. But this all was like extremely robust in that case, in that context. And you can also do something like this with cameras based on LiDAR point clouds. So here you basically see a paper that we published a few years ago, where we localized a monocular camera relative to a 3D point cloud rendered with a LiDAR scanner, right? In this case, a Velodyne, and the question then was, like, how accurate can we localize a smartphone or other type of cameras relative to such a 3D point cloud? But the advantage would be that for localization, then you don't need basically an expensive LiDAR anymore. You can potentially do this with your dashboard camera. And the idea there basically is to reconstruct 3D points from visual odometry, and then perform, in this case, ICP plus a nonlinear least squares optimization to get the 6DOF camera pose. And yeah, so see the key approach here. And with this, you can then basically, by matching the point clouds extracted from the camera image to the LiDAR point clouds, you can perform localization of cameras in also dynamic scenes like the Kitty data set over here. The interesting aspect is by this approach, you get a little bit independent of the appearance, because you basically reconstruct these data points, or these points from the moving camera, which allows you also to deal with different seasons, for example, or other changing conditions. So that is, or varying conditions. So we created a so-called Freiburg campus data set where we used a robot to record a 3D point cloud, and by installing the cameras on the robot, we actually also knew some of the ground truth of these camera poses relative to the map generated with the SLAM approach on the robot. And so here you can basically see the accuracy of the camera localization for over 10 runs with 2 different cameras. And here is some visualization of this data set. You can basically see how the camera is being tracked over in this map. And we also reproject the colors onto the mesh that we reconstructed, on the point cloud. And the reason that the tree canopies are white is that the branches like change their positions. So by reprojecting through the wind, so in most of the cases, and they are extremely thin as well. So most of the cases, like the sky color is projected onto the branches of the trees. This is why they have this the sky color. And of course, that is like one aspect that is being done or that is relevant for autonomous vehicles. these type of localization approaches. And on the other hand, they typically, and Torsten mentioned that before, require that what is called HD maps created from some sort of SLAM approaches. And there are different ways for do this. This is a particle filter based approach, but then you can also use optimization based techniques. And here in this case, this is just an occupancy map, but you can also use these optimization based approaches, and you all know this, I guess, to basically calculate accurate maps on the fly. And this is what we are right now doing in robotics, basically building these or optimizing these maps while we are navigating through the environment. The assumption is that we can always robustly solve the data association problem. So this is, you can also do this offline, and then also go wild if you want and start with 0, 0 and a random angle, and then reconstruct the trajectory if you're lucky, as in this case. So, and with this, you can then build 3D representations. Some companies use meshes, as you see here. Others use point clouds as representations, with the disadvantage that they are actually extremely expensive in terms of storage. So this is why people actually look into alternatives, which are basically that what is called HD maps for automated driving, which is something that you see here on the top, which are basically sparse representations or sparse features that you can observe, like lane markings, which is just like lines or linear structures. And then you have poles, which are just basically positions in the map that can be efficiently stored in order to actually use them in localized vehicles. But they're not only useful for localization, since they are also relevant for perception. So when you look at, for example, on the lower right-hand side, so this is a picture that I found on the Google webpage. This basically is the ground that is represented as a point cloud, and by subtracting this point cloud from your LiDAR observations, you basically get immediately out, can easily crop out all the objects that are on top of the ground, and even have a better segmentation and all these kind of things. So this is one aspect that you need to do in HD maps in order to actually, one way to use HD maps for. The other one is even more expensive. These are basically representations where you need to represent the topology of the road that allows the vehicle to understand from where to where it can actually go in an intersection. And also another important aspect is where for example, traffic lights are, and how they are associated to the individual lanes. Right? So this is also an important problem. Like if you make a false data association between a traffic light and a lane, then the car might do a wrong decision. And so that is why these HD maps are so enormously important. You can even use them for predictions. Once you know where the lanes will go, right, then you can actually make proper predictions or better predictions about where an ADO vehicle might, for example, go. However, maps come with limitations, and they come from dynamic environments, changes, information beyond geometry, right? Semantics, and then the question like how we react to these changes, and then even more, can we infer maps on the fly? And this is something I would like to discuss at the very end of this presentation. So challenges for HD maps, and here is one. Right? So assume that we do have these type of HD maps that represent lane markings, and in order to localize the vehicle. And this is a video recorded in Michigan Ann Arbor during winter, and where you can basically see that the majority of these features that you would expect to see given your HD map are basically not visible anymore. And that is an extreme challenge, but doesn't need to be that dramatic challenges or changes. So it could even be like, if you look at the bottom, this is a Waymo car being stuck on the road, where basically, because there's a construction going on, people put cones onto the road, and the car actually doesn't know how to interpret this information and what to do with this. And so like even what you can see from this is that even slight changes to the map might have catastrophic consequences, basically that the vehicle is not able to move anymore. And and this is why it is important to understand that maybe this entire idea of building maps and then navigating around is not the one that will get us to robust level 4 and maybe even level 5. So for level 5, it is even more challenging, because for that, there you basically need to have the ability to react or to drive based on your most recent sensor data. And this is a substantial challenge. And the key question is how to basically achieve this. And from my perspective, like there are several ways. Like one is change detection. Like if you want to rely on HD maps, and then you need to have the ability to figure out that something has changed. And that is an important aspect. And you don't want to do this, for example, with these expensive vehicles that are currently used by companies and sent around in order to map the environment. You do not want to drive every day through your level 4 geofenced area in order to basically detect as to whether the world has changed. And certain OEMs, and particularly those who have the ability to have fleets available already on the roads, they are thinking right now about how to use the sensors from their advanced driver assistance systems, camera, for example, for detecting changes. And this is something that we also explored in this work with David Pannen and colleagues from BMW to actually try to figure out as to whether a map has changed. And that the idea that using fleet data makes sense, that's something that you maybe like, I can maybe convince you about when you look at these figures, where you basically see the density of the fleet of BMWs recorded during a day, and the heat map of where they are. So there's a substantial potential for basically figuring out as to whether something has changed using fleet data. Key question is how to do this, and given the ADAS systems, you typically have to rely on very restricted information, which would be, for example, GPS information, odometry information, and then observed lane markings and road edges, for example. And then what you can do mostly is compare this to what you do have in your HD map, namely lane markings and road edges. And then you can use such information, for example, like in a vehicle, like extract this on the fly and like estimate all these features while the vehicle is driving here in the vicinity of Munich in this case. Key question now is, how do you figure out that a difference that an individual vehicle observed is actually a change in the environment that would require a potential remapping. And so one idea is, or that what we implemented in this case was basically to look at a particle filter trying to track this vehicle and trying to figure out like trying to look at the innovation, or basically the likelihood of these perception and the detected features given the predictions that come from the HD map, right? And there we, as I mentioned, we used odometry, GPS information, lane markings, road edges, and then we basically used a classifier trained from supervised data where we basically took the vehicle and drove it through construction zones so that we could actually figure out and exactly know that where the vehicle would supposed to report a change or not. And then we actually had used bins along the road and let the classifier then vote for every bin as to whether it thinks that there's a change or not. And then depending on the majority of the votes, can then actually have a voting for the innovation detection. And here you can see like this in action. So you basically see the individual bins along a German highway section. What you can see is that it moves from green to red over there, where you actually see a change in the lane structure. Interestingly, and as maybe for computer vision people important, so the system should report the construction zone already here, but as we don't use color information in our current system, so and don't distinguish between yellow and white, the road markings, the system actually is still quite happy here in this area, although the yellow lines indicate, at least in Germany, that this is there's a construction zone going on, and that also actually corresponds to a change. So this is a way of how to basically use like fleet data with low-cost sensors for detecting something like this. And if you look at as to whether and investigate as to whether it actually makes sense to use like fleet data, then you can see this how the the difference between single trace classifications and multi-trace classifications improves over with the number actually of traversals of that area. But the key question is like is there a chance to maybe potentially go completely get rid of these type of HD maps? If we are able to do this, then we basically save a lot of money, because creating these maps is enormously expensive. And from that perspective, at least my view on this is that yes, there is a potential, but that would require that we have the ability to understand that what we observe. So basically, we need to go deeper into understanding semantics and the dynamics of the world, and also in order to also make predictions. And this is some work that we started to look into recently, this panoptic segmentation and tracking piece of work, where we are basically trying to understand like what is what in the world and where are things going. And yeah, this is like basically, and you want to do this for all modalities that you have. So this is the input then for a car, or basically the LiDAR input, and you want to interpret this and understand what's going on in the world and what are all the things that I see. And yeah, popular approaches, and I don't think I need to go into details here, is segmentation, semantic segmentation, and then you can like combine this with instance segmentation and basically get that what is called panoptic segmentation, right? In fact, there are these benchmarks, and you need to come up with new architectures there. And here are a few new architectures that we developed when we created this work, and also like different kinds of components. But let's look at the evaluations here, and this is maybe closer to that what's typically done in CVPR type of settings, where we basically take these data sets, and Torsten presented this as well, and compare your approaches relative to these data sets. And we use semantic kitty and useens for this. And at the time where we published the work, we were actually #1 on the corresponding leaderboards. But this is now gone, and this is also good. Like people kept working on this, and there are better approaches out there. But what I want to mention is that this type of work, from my perspective, is also worth being pursued, because what we have seen before was like basically creating geometry and then using the geometry to figure out where the vehicle is and then make decision based on this. The question is, do we actually need this? And like it is limited, because it doesn't allow us to do everything and make proper predictions about the world and so on, and understanding the world. So here is a potential output of this, and the fact that the cars actually change their colors is the reason that, again, we do this based on just one individual observation, and we do not track these and our perception or the individual cars over time. And that is then like that what leads to the combination of panoptic segmentation and multi-object tracking, which then leads to this technique of multi-object panoptic tracking. And basically that what we are interested in is having color consistency over time while the vehicles are moving. And again, need to come up with a proper architecture if you want to be better than the state of the art, which we achieved at that time as well for Kitty and for the semantic Kitty, and the virtual Kitty 2 for vision-based approaches. And here are vision-based and then also the LiDAR-based results at the time when we published the paper. I think the interesting aspect here is this video showing the performance of the system. It's not perfect. In some cases, the color, like of this minivan, there are changes. So there's still space for optimization, but there are better methods out there right now. But I think these type of work will allow us to actually get rid of all these HD maps and understand the world based on that, what we basically get from our sensors, and then also use this type of information to generate actions. And the performance measurement, then this is the advantage of self-driving cars and robots in general, would be the number of interventions that you need to do, and you do not need to think that much about ground truth. So all you need to do is to look at the performance of your vehicle in the real world. Yeah, here's another interesting, nice visualization of on the right hand side. You see the color consistency of the tracked objects. And yeah, here's another video where you can basically also see this in the context of moving objects, and the car approaches this intersection. There's greenish tornado. There's other vehicles that are being tracked in the individual scans. At the end, I want to talk a little bit also about another problem that we have been looking into, namely the fact that these data sets that we see thus far mostly focus on relatively moderate scenes, but it gets more difficult when you, for example, look at completely different areas where cameras basically have enormous problems. And this is, for example, night scenes, and how we can actually properly deal with night scenes. This has two aspects. The first one is the problem itself, and the second one is labeling nighttime images. It's extremely tedious, and my students were complaining a lot about the huge amount of work that it requires to basically properly label a nighttime image, because basically what you're faced with is dark pixels, and figuring out what that is extremely hard. And on the right hand side, you basically see a standard CNN trained on a publicly available data set for daytime images for actually tracking objects, or for the semantic segmentation, sorry. And so here you can see and that's what we use for this. Is a thermal camera, which, as we figured out, or as we expected, also has a substantially smaller domain gap between day and nighttime. And then what we basically did is we used
Sorry, could you say that again? Oh. My apologies. I couldn't hear what you said.
Give me a second. My cell phone is too autonomous here. So basically what we had is like an RGB teacher network, and we trained our heat net in a way that it produced an output that corresponds to these segmentations that typically the teacher network generates. And that is basically what we did in this context, and did this with modifications also for the nighttime domain. What is interesting then, this is a vehicle that we used to record the data set. You see the thermal camera over here, and then we also had a stereo pair of RGB cameras. Created a data set like that you find down here, where you basically see the thermal images on the right hand side, different conditions, and evaluated then the performance of our heat net on different on an evaluation data set. The results are pretty interesting. So that what you can see in the bottom right here is the output of our RGB thermal network compared to the RGB teacher, and on the right hand side you see the ground truth. Turns out that, as you see, it produces substantially better results on nighttime images. The interesting aspect is that you can, even at a runtime, remove the thermal component and just run the RGB component on the nighttime images, and it still produces better results than the RGB teacher. Which is interesting, because that would potentially allow you to use the thermal camera only during training and then get rid of it during evaluation or application, which means that you can then use the RGB camera in a standard vehicle. And RGB cameras are substantially less expensive than thermal cameras. So that's in particular an interesting pathway towards like the cost reduction that you find, or the necessary cost reduction that you find in automotive industry. Here's an application of this at in Freiburg data set for starting at daytime, and later on it becomes it gets dark as well, and still you can actually like nicely segment out bicyclists and so on and so forth. And at the very end, just very briefly, a very recent work that where we actually try to infer the road topology from multiple modalities in bird's eye view form, and the idea there basically is to have the lane graphs and directions inferred from these images that you see on the left-hand side, so that the vehicle would actually be able, from just looking at an image of a road, decide where it can actually go. Right? And again, in lane graph net that we use to then infer the directional lane graph. And here you can see some results. On the left-hand side is always ground truth. On the right-hand side is the result of our approach. As you can see, it performs pretty well, not in all cases, but I think it is the right way to go. It is not as good as I had hoped for intersections, which are the major problems there. And they are extremely expensive to basically create these intersection graphs. And this is something that we are working on as well, trying to infer the topology of the roads, which then would basically substantially ease the creation of these maps, and maybe even could be something like another component needed for level 5. Yes, so to the end, I think like what we see right now is like people having these geometric approaches and trying to build maps and then localize relative to these maps, where these probabilistic approaches are like pioneering and actually pretty robust and accurate, at least in robotics. And on the other hand, there's this machine learning that promises us right now to maybe take a next step towards getting rid of all these maps with challenges, data bottleneck, labeling efforts. And the key question that I would like to understand in the future is like, if we are able to infer these maps on the fly, right? Is there a way to actually get rid of the maps? That's it. Thank you.
All right. Thanks a lot for the very interesting talk. I've covered a lot of interesting topics related to autonomous driving. And I would start with one question, if I may, also like to your conclusion slide. The last point, I think, is a very interesting point, because today in the speakers, we also had Kendall. He's heavily advocating the end-to-end learning pipeline without using an explicit map representation. And you've been also talking about in your talk about relying on HD maps. So the question is, first of all, do you think it makes sense that we can leverage the advantage of both worlds somehow together, instead of saying we need HD maps, or we can do it end to end? Is there any way you think we can basically fuse the ideas and leverage advantage of both worlds?
Yeah, that's a great question. So first of all, I'm not religious in this context. I'm a researcher, and I think with this idea of using HD maps has brought us very far, right? In if you look at self-driving cars, like many of these companies rely on this, and we do have like logistics applications that rely on maps and localization and so on and so forth. I think the idea of doing all of this end to end is right now not as far, and also I think we are relatively far away from applications there. At least I don't see them directly, right? I mean, there are companies that use a restricted form of maps, maybe SD maps or so, right? So, which is also interesting, something in between, but going completely end to end is probably quite a challenge right now. And I would regard this more on the side of research. And this is how I also think that should be considered here. This is something that, or that would be like my answer to this. I think we shouldn't say A or B here in this context and basically wait for science to and researchers to help us understanding more how this works. And I'm also interested in understanding maybe what representations could be, and as to whether we will ever find a representation that allows us to navigate a robot around without like a map, and also like telling it exactly what is what in the world.
Okay, thanks. That's a very good answer, I would say. I have a question also regarding, you mentioned that sometimes you can use a fleet for change detection, right? So if you use a fleet of cars, you can use the sensor modalities for change detection. So like, how far do you think we are away from using the sensor data from such a fleet to also do automatically or semi-automatically update the HD maps?
Yeah, that's, I mean, that has two aspects. I mean, to a certain extent, companies, I think like Google does this right now already, right? They're extremely fast in figuring out construction zones just from observing where vehicles go. And they also know where, for example, traffic jams and so on and so forth. I think that has great potential, and I would hope that we in the future can actually leverage something like this as well. But it also comes with this risks, right? So for example, if you think about that someone always like drives over the sidewalk like every night and intentionally when no one is there, and then all of a sudden all cars think that the road now goes over the sidewalk, right? And that would be like a potential threat, and so we need to be very careful in doing something like this. And yeah, but I think like technically it is an interesting question, and I believe that it's definitely worth looking into this, but we need to be aware of the potential limitations there.
Okay, thanks a lot. There's also a lot of research in like how an HD map should be comprised. So what kind of features it should contain? Do you have some takeaway from your personal experience, like what you believe are really like key ingredients for an HD map to drive autonomously? Like what is really necessary?
I think that definitely that what you need is you need to know where the lanes are, you know, if and where the road edges are. So I mean, there's this thing like stay on the road, right? And if you want to rely on post estimates for doing this task, then you need to know where the road edge is, and also maybe the lanes in order to stay on the lanes. And further important and very critical aspect is this data association between traffic lights and lanes, so that the car doesn't think that a different traffic light is responsible for its lane, so that it doesn't enter the intersection when it's actually red. And then the next one is topology of intersections. This is an extremely difficult problem, like how to properly go through an intersection. And for that, there's currently, even if you think about the ability to detect the lanes or the lane markings and stay in their lane, there are assistants right now, but they don't work in intersections, and with reasons, because they are simply too complicated.
Okay, thanks a lot for the answers, and thanks a lot for being here in the workshop and for giving this great talk. With that, I would like to conclude our workshop. So I would like to thank everyone for joining the workshop. I would like to use this opportunity to thank all the speakers again who spoke today at our event. Also, I would like to thank the invited talks from the challenge. And with that, I would like to wish everyone a nice rest of the week for ICCV. And thanks a lot for joining, everyone.
Thanks for the invitation. Goodbye.
Thank you. Bye-bye. Have a nice evening.